Hello there, and welcome to the Cosmographer. In 2018, a telescope in the Australian desert recorded an object in our own galaxy pulsing every 21 minutes. On a clock, the physics of dead stars says it cannot keep, and the archives showed it had been doing so, unrecorded, since 1988. That is only number 8 on this list. Further down is a single particle that struck the atmosphere over Utah, carrying the energy of a thrown baseball, arriving from a direction where the maps show nothing at all. Below that is an axis printed into the oldest light in existence, lying uncomfortably close to the plane of our own planet's orbit. Further down still are 2 measurements of the expansion of the universe, each accurate to about 1%, that disagree by 9. The entry at the top is first for a reason that has nothing to do with how far away it is. 10 mysteries, counted down from 10 to 1, ranked by how far beyond the edge of what we can observe the answer has to lie. Get comfortable and settle in. If a long walk through what science has not solved sounds like a good night to you, a quiet like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, the edge of space will not look like a boundary anymore. It will look like a limit of eyesight. Let's begin at number 10. Number 10. The rings nobody ordered. The edge of space is not a wall. That is the first thing to settle, because almost every picture of it is wrong, and the 10 entries on this list only make sense once the picture is corrected. There is no boundary out there, no membrane, no far surface where the universe stops and something else begins. What exists instead is a horizon, and a horizon is a statement about the observer rather than about the landscape. Here is how that horizon is built. The universe is roughly 13.8 billion years old, and light travels at a fixed speed. Light emitted at the very beginning has therefore had 13.8 billion years of travel time, and nothing beyond that reach can have reached us yet. But space itself has been expanding during the journey, carrying the emitting objects further away while their light was still in transit. When the arithmetic of that expansion is done properly, the objects whose oldest light is arriving now sit about 46.5 billion light-years away. That gives us a sphere roughly 93 billion light-years across, containing something on the order of 2 trillion galaxies. That sphere is not the universe. It is the portion of the universe from which information has had time to arrive. Everything outside it is presumably more of the same, going on indefinitely, and it is invisible not because it is hidden, but because the light has not finished the trip. Every day the sphere grows a little, and every day a certain amount of it slips permanently out of reach as the expansion accelerates. The edge of space, in the precise sense, is a moving accounting boundary in the arrival of light. There is a second, looser sense of the phrase, and it is the one this list actually lives in. That is the observational frontier, the outer limit not of what light has reached us, but of what our instruments can detect, resolve, and identify. That frontier sits far inside the true horizon for almost every kind of observation. It is where the data becomes thin, where the categories run out, and where the honest answer to a simple question stops being a theory and becomes a sentence about the limits of what we can see from inside. The 10 entries ahead are ordered by a single measure. They are ranked by how far beyond the edge of what we can observe the answer must lie. Number 10's explanation is probably a few 100 million light-years away and probably reachable with a better telescope in someone's lifetime. Number 1's explanation is not anywhere in space at all. It sits in a time no living person will reach, and that is why it is first. The list travels outward, entry by entry, from mysteries whose answers are merely distant, to mysteries whose answers lie in populations we cannot pick apart, to mysteries whose answers lie in the opening conditions of the universe itself, and finally, to the one whose answer lies past every horizon we have. We begin with an object that was not predicted, was not expected, and did not exist as a category until 2021. In the western desert of Australia, there is a radio telescope called the Australian Square Kilometre Array Pathfinder, usually shortened to USCAP. It consists of 36 dish antennas, each 12 meters across, spread over about 6 kilometers of red ground at a site chosen for its radio quiet. Its purpose is survey work. It was built to map enormous areas of sky quickly, rather than to stare at single objects. And its flagship project, the evolutionary map of the universe, is designed to catalogue something on the order of 40 million radio sources. The previous catalogue of the radio sky contained roughly 2.5 million. When a telescope increases the size of a catalogue by a factor of 16, it does not simply find more of the same things. It finds things that were never in the catalogue at all, because they were too faint, too large, or too unlike anything the search was written to expect. That is what happened here. In the pilot survey data, taken at frequencies between about 800 and 1088 megahertz, a team led by Ray Norris found a small number of objects that did not match any known class. They were rings. They are called odd radio circles, and the name has stuck, abbreviations and all. In the literature, they are AUX. What they look like is exactly what the name suggests, a circle of radio emission, bright around its rim, faint in the middle, remarkably close to perfectly round. A rim that is bright while the interior is faint is a specific signature. It is what a hollow shell looks like when you photograph it, because a line of sight through the edge of a shell passes through more emitting material than a line of sight through the middle. So these objects are not disks. They are spheres, or something very close to spheres, and we are seeing the outsides of them. The first one was catalogued as AUK J2103-6200, and it is now generally called AUK-1. A second was recovered in archival data from the giant Metro-wave radio telescope in India at 325 megahertz. Both were reported in 2021. A third, AUK J0102-2450, was announced the same year by Barbel Korybalski and colleagues. A fourth arrived in 2022, a fifth in 2025. Since then, an automated object detection search run over the first year of the full survey has turned up several more, and the count keeps rising. Now the numbers, because the numbers are where this stops being a curiosity. Each of these rings is about 1 arc-minute across on the sky. An arc-minute is 1/60th of a degree, which makes it roughly 1/30th the apparent width of the full moon, and it is very close to the smallest thing an unaided human eye can resolve. On the sky, in other words, they are tiny. What matters is how far away they are. Almost every ORC has a large elliptical galaxy sitting precisely at its center, and those galaxies have measurable redshifts, which give distances. The redshifts cluster around 0.2 to 0.5, placing the rings somewhere between roughly 2 and 5 billion light-years away. At those distances, 1 arc-minute is not small at all. Take AUK J0102-2450. Its host is a central elliptical galaxy at a redshift of about 0.27. The measured ring diameter is about 70 arcseconds, which at that distance works out to roughly 300 kiloparsecs. In planar units, that is very close to 1 million light-years across. Hold that against something familiar. The stellar disk of the Milky Way, the bright part containing essentially every star anyone has ever named, is about 100,000 light-years wide. This ring is 10 times that. Whatever process created it swept a shell 1,000,000 light-years in diameter around a single galaxy, and then left nothing behind that any other instrument can see. That last point deserves its own paragraph, because it is the core of the mystery rather than a detail of it. These objects are invisible at every wavelength except radio. There is no optical counterpart. There is no infrared counterpart. There is no X-ray counterpart. Point the best optical telescopes at the position of an ORC and you see the host galaxy at the center and nothing else. No shell, no shock front, no glowing gas. The ring exists in radio waves and in radio waves alone, which means whatever is emitting is not hot gas and is not starlight. It is synchrotron radiation, electrons moving at close to the speed of light, spiraling along magnetic field lines. The measured radiospectral index is steep and negative, typically below -0.4, and a steep negative index is the fingerprint of an aged electron population. These electrons have been losing energy for a long time. The rings are old. So the situation is this. Something happened at the center of a massive elliptical galaxy, some large number of millions of years ago. It drove a spherical shock outward to a radius of 500,000 light-years. That shock accelerated electrons and organized a magnetic field well enough to produce a clean, bright, almost perfectly circular rim. And it left no other trace of any kind. The proposals are numerous, and none of them is settled. The first is a termination shock from a galactic outflow. A starburst in the host galaxy drives a wind. The wind expands, and eventually it stalls against the surrounding medium and forms a shell. That works geometrically, but has trouble with the size and with the sharpness of the rim. The second is the merger of two supermassive black holes at the galaxy's center, releasing an enormous pulse of energy in one event, which drives a spherical blast wave. That would be a satisfying answer, and it would make orcs the fossils of an event we have never directly witnessed. The third is an accretion shock at the virial radius of the host galaxy's dark matter halo, essentially the boundary where infalling gas piles up, lit by some triggering event. The fourth, offered for a particular ring near the Large Magellanic Cloud in 2022, is an intergalactic supernova remnant, which would make that one object a member of an entirely different family that only looks similar. Cosmological simulations have been run against the problem. A 2022 study produced ORC-like shells from galactic outflows but could not reproduce the sharpness of the edges. A shocked wind interpretation was published in late 2025. Shock bubble interaction models followed in early 2026. Every model can make a ring. No model yet makes a ring of exactly that size, with exactly that brightness profile, and no counterpart anywhere else in the spectrum. Two further details complicate matters, and both arrived recently. The first is a deep polarimetry study published in 2025, which found double ring structures, two concentric rims rather than one. A single expanding shell does not easily produce two concentric rings. Either there were two events, or the geometry is something we are reading incorrectly. The second is a meerkat search toward the plane of our own galaxy, which turned up 164 compact radio rings. That raises an uncomfortable possibility, that a ring of radio emission with nothing inside it is not one phenomenon, but several unrelated ones that happen to share an appearance, and that we have been trying to build one explanation for a category that does not exist. There is a phrase worth carrying forward from this entry: because it will come back later on this list in a much sharper form. The universe does not owe us a source. We are accustomed to a particular sequence in astronomy. You see something unusual, you look at the same place with other instruments, and you find the object responsible. That sequence has worked so reliably for so long that it feels like a law. It is not a law. It is a habit, and it holds only as long as the object responsible happens to emit in a band we can detect. The AUX are the polite version of this problem. There is a shell. It is 1,000,000 light-years across, and there is nothing at any other wavelength to tell us what made it. And there is a second phrase, which is the ranking axis of this entire list, stated in miniature. The answer is further away than the object. The ring itself sits 2 billion light-years out, which is far. The explanation for it sits further, not further in kilometers, but further in the sense that matters, which is the number of things that have to happen before anyone can go and check. There is one more feature of these objects that is easy to pass over and worth sitting with. A synchrotron ring is not only a detection of electrons, it is also necessarily a detection of a magnetic field, because electrons cannot radiate that way without one to spiral around. So every ORC is a measurement of an organized magnetic field 500,000 light-years from the center of a galaxy, in a region where the gas density is close to nothing and where there is no obvious machinery for organizing anything. Magnetic fields at that scale are among the least understood features of the universe. They are difficult to generate, difficult to maintain, and difficult to detect, except by exactly this kind of accident. Nor do these objects change. Every ORC ever imaged is a still photograph. The processes involved unfold over millions of years, so no ring has ever been seen to brighten, fade, expand, or move, and none ever will be within any human observing program. Everything we know about them has to be extracted from a single frame, which is one of the reasons the modeling is so difficult. Astronomers usually work out what something is by watching it do something. Here there is nothing to watch. It is also worth noting where at least one of them was found. AUK J 1555 plus 2726 was not discovered by a new observation at all. It was recovered from archival data taken years earlier with the giant Metrowave radio telescope, sitting in a public dataset, unremarked, because until the category existed, nobody had a reason to call it anything. That is a pattern this list will return to more than once, and it is one of the quietly unsettling features of modern astronomy. A large fraction of what we do not yet know is not waiting to be observed. It has already been observed and filed. For this entry at least, that gap is closing. The AUX are the nearest thing on this list to a solvable problem. There are more of them being found every year. The square-kilometer array is under construction and will find hundreds more, and one of the proposed mechanisms will eventually fit. Somebody currently working will probably know the answer. That is the last time on this list that sentence will be true. At least the rings are far away, and their strangeness stays comfortably at a distance of billions of light-years. The next entry sits 190 light-years from here, in a constellation you can find with a small telescope, and for most of a decade, the best measurement anyone could make said it was older than the universe containing it. Number 9. The star that was older than the universe. In the constellation Libra, there is a star of about 7th magnitude, which means it is invisible to the naked eye and easy in a pair of binoculars. It has no proper name in any classical tradition. Its catalogue designation is HD 140283, and it sits about 190 light-years away, which by the standards of this list makes it practically a neighbor. It is not large, not bright, not variable, and not doing anything unusual. In every observational respect, it is one of the most boring objects on this list. Its informal name is the Methuselah star, and for the better part of a decade, it was the cleanest single example in astronomy of a measurement that contradicted the age of the universe. Start with what makes it interesting in the first place. Stars are chemical records. The first generation formed from hydrogen and helium and almost nothing else, because nothing else existed. Everything heavier, carbon, oxygen, silicon, iron, was manufactured inside stars and returned to the interstellar medium when those stars died. So each new generation of stars forms from gas slightly richer in heavy elements than the last, and a star's chemistry is therefore a rough clock. Astronomers call all elements heavier than helium metals, which is chemically sloppy but universally used, and a star with very few of them is described as metal poor. HD 140283 is one of the most metal-poor stars ever found in the solar neighborhood. Its iron content is on the order of a few 10,000ths of the Sun's. Gas that poor in iron had been enriched by very few previous generations of stars, which means this object formed early, plausibly within the first few 100 million years of cosmic history. Its peculiarity was noticed remarkably long ago. In 1912, Walter Adams recorded that its spectrum did not look like other stars of its type. In the 1950s, Joseph Chamberlain and Lawrence Aller used it, and one other star, to demonstrate that some stars are dramatically deficient in metals compared with the Sun. That paper is one of the founding documents of the idea that the chemistry of the galaxy has changed over time. This star has therefore been under continuous professional observation for more than a century. It is not a marginal detection at the edge of a survey. It is one of the best studied stars in the sky, and that is exactly why the problem it created was so difficult to dismiss. Now the measurements, in order, because the order is the story. An early analysis placed the star's age at around 16 billion years. The universe, as measured from the cosmic microwave background and the expansion history, is 13.8 billion years old. A 16-billion-year-old star inside a 13.8-billion-year-old universe is not a small discrepancy that can be smoothed over. It is a contradiction, and the profession treated it as a sign that something in the stellar modeling was wrong, rather than as a sign that cosmology was wrong. In 2013, Howard Bond and collaborators attacked the problem at its weakest point, which was the distance. Everything about a star's inferred age flows from its luminosity, and luminosity requires distance. They used the Hubble Space Telescope's fine guidance sensors to measure the star's parallax, the tiny apparent shift in its position as the Earth moves around the Sun, to a precision of roughly 5 micro-arcseconds. To put that precision in ordinary terms, it is comparable to measuring the angular width of a coin in Los Angeles as seen from New York. With a trustworthy geometric distance, the star's luminosity was pinned down, its position on the theoretical evolutionary tracks was pinned down, and the age came out at 14.46 billion years, with a stated uncertainty of about 800 million. Read that carefully, because the headline and the fine print say different things. The headline number, 14.46 billion, is still older than the universe. The fine print, plus or minus 800 million, means the true value could be as low as 13.66 billion, which fits inside cosmic history with a little room. The star was not proof of anything. It was a measurement whose central value was impossible and whose error bar was just wide enough to rescue it. Then the numbers moved again. In May of 2021, a group used the Pavo beam combiner at the Cara array to measure the star's radius by interferometry, combining the light of several separated telescopes to resolve a disk that no single telescope can resolve, and fed that radius into modern stellar evolution modeling. Their revised age was roughly 12 billion years. That is not a small correction. It is a reduction of about 2.5 billion years, and it moved the star comfortably inside the universe. In 2024, another group ran the calculation again, using models with element abundances tailored to this star's own peculiar chemistry rather than a standard scaled mixture. And in 2025 came the most direct measurement yet, an asteroseismic study. Asteroseismology works by detecting sound waves trapped inside a star, which cause the surface to brighten and dim by parts in a million on characteristic timescales that depend on the interior structure. It is the nearest thing available to looking inside. That study returned a mass of 0.75 solar masses, a radius of 2.078 solar radii, and an age of 14.2 billion years, plus or minus 0.4, described by its own authors as consistent with the age of the universe within one standard deviation. So the sequence, in full, runs like this: 16 billion, then 14.46 plus or minus 0.8, then about 12, then 14.2 plus or minus 0.4. 4 careful measurements of one nearby, bright, well-behaved star, made by competent people using the best instruments of their respective decades, spanning a range of 4 billion years. The star did not change during that period. It has not measurably changed in a million years. What changed was the model. That is the actual content of this entry, and it is worth being blunt about it. The age of a star is not observed. It is inferred. What you observe is brightness, color, and the pattern of absorption lines in the spectrum. What you infer is everything else, and the inference runs through a computational model of how energy is generated in the core and transported to the surface. The single largest source of uncertainty in that chain is convection, the turbulent, three-dimensional boiling motion that carries heat through the outer layers of a star. Convection is genuinely difficult. In almost every stellar model in use, it is represented by a single tunable number, called the mixing length. Adjust that number within its plausible range, and the inferred age of a subgiant moves by 1 billion years or more. Adjust the assumed helium abundance, and it moves again. The 2021 revision to 12 billion years came substantially from a better radius, combined with a different treatment of convection. Here is why that belongs on a list of mysteries beyond the edge, rather than in a footnote about stellar physics. We have 2 independent clocks for dating the universe, and they were calibrated separately. One is cosmological, the microwave background, the expansion history, and the fitting of a 6-parameter model. The other is stellar, the ages of the oldest stars and the oldest globular clusters. Those 2 clocks have never fully agreed, and every time they have been brought into agreement, it has been by moving one of them. This has happened before, at a much larger scale. In the 1990s, the oldest globular clusters were being dated at 15 to 18 billion years, comfortably older than the universe of the day. That was a genuine crisis, discussed in exactly those terms. It was resolved in 1998, not by fixing the clusters, but by the discovery that the expansion of the universe is accelerating, which made the universe older than the previous model allowed. An entire component of the cosmos was added, in part because the stars were too old. And now consider the hypothetical, clearly labeled as speculation, because it is the reason this entry sits where it does. Suppose a future measurement of a metal-poor star returns an age that survives every model revision, every convection treatment, every abundance adjustment, and still exceeds the age of the universe by more than the combined uncertainties. The resolution would not be that the star came from somewhere else, or that it formed before the beginning. There is no mechanism for either. The resolution would be that the universe is older than 13.8 billion years. That is not an idle possibility. It is one of the live proposed resolutions of the disagreement waiting at number 3 on this list. The two measurements of the expansion rate that cannot be reconciled imply different ages for the universe, and the difference between them is roughly 1 billion years. The oldest stars are one of the few independent handles on which answer is correct. So HD 140283 is not a rogue object. It is a witness in a case that is still open, and it has been giving inconsistent testimony for 60 years, not because it is unreliable, but because the questions have kept changing. It is worth pausing on why this particular star, out of the hundreds of billions in the galaxy, ended up carrying so much weight. The answer is that it is a subgiant, and subgiants are the best natural clocks we have. A star spends most of its life on the main sequence, fusing hydrogen in its core, and during that long stretch its brightness barely changes, which makes its age nearly impossible to read. When the core hydrogen runs out, the star begins to expand and cross toward the red giant branch, and during that crossing, its luminosity changes quickly and predictably. Catch a star mid-crossing, and you can date it far more sharply than at any other point in its life. HD 140283 was caught mid-crossing, close enough to measure directly, and metal-poor enough to be genuinely ancient. There is no better placed object anywhere in the sky, which is also why the disagreement mattered so much. If the numbers had come from a faint star in a distant cluster, everyone would have shrugged at the error bars. They came instead from the single most favorable case available, measured by people who understood exactly what was at stake, and the answers still spread across 4 billion years. If the best case behaves like that, the general case is worse. The distance, at least, is now beyond argument. Hubble's parallax was confirmed independently by the Gaia spacecraft, which has measured the positions and motions of nearly 2 billion stars with a precision no previous instrument approached. The one input that could have been quietly blamed for everything has been checked twice by different methods and found to be correct. Whatever is unstable in the age estimate, it is not the geometry. It is the physics of the interior. And the star is not alone. There is a whole population of metal-poor halo stars whose ages cluster uncomfortably close to the age of the universe, and there are the globular clusters, which are better statistically because each contains hundreds of thousands of stars that all formed at the same time. When you fit a whole cluster at once, individual stellar oddities average out and the age estimate tightens. The oldest globular clusters currently date to somewhere between about 12.5 and 13.5 billion years. That is comfortable, but only just. There is not much room in the schedule. The universe forms, the first stars light up a few 100 million years later, and the oldest objects we can still see today are already assembling. A universe even 1 billion years younger than the standard figure would compress that sequence to the point of real difficulty. There is a phrase that gets used about this, and it is more precise than it sounds. The age of the universe is not a measurement, it is a fit. It is the number that comes out when a model with 6 free parameters is matched to the pattern of the oldest light. Change the model and the number moves. The oldest stars are the only completely independent check we have on it, and they have been quietly disagreeing within their own uncertainties for as long as anyone has been careful enough to notice. One more detail closes the picture. Asteroseismology, the technique that produced the most recent number, works by listening rather than looking. Sound waves generated by turbulence near the surface travel down into the star, refract, and return, and different waves probe different depths. By measuring the frequencies of those oscillations, you can read the density profile of the interior directly, which is the one quantity every age estimate depends on, and no other method can access. The brightness variations involved are on the order of parts per million, and detecting them at all in a star this old required years of patient photometry. That the answer came back at 14.2 billion years, plus or minus 0.4, is either a reassurance or a warning, depending on which way the age of the universe eventually moves. A few more things about it are worth knowing. It is not a resident of the galactic disk. It is moving through the solar neighborhood at about 360 kilometers per second on a plunging orbit that marks it as a halo star, one of the population that surrounds the galaxy in a roughly spherical cloud rather than orbiting within the flat disk. It is passing through, not living here. Its surface temperature is about 5,780 Kelvin, which is almost exactly the Sun's, and part of why the comparison between the two is so clean. And despite the metal poor label, it is not a first-generation star. It contains iron, which means at least one generation preceded it. No genuinely metal-free star has ever been found, anywhere, by anyone, which is a small mystery of its own that nobody has adequately explained. Within a few 100 million years it will leave the subgiant branch, swell into a red giant, and end a life that has run for essentially the entire history of the galaxy. Nothing will mark the occasion. That star, at least, is behaving consistently. It sits where it has always sat, doing what stars do, and only our description of it has wobbled. The next entry on this list is a set of objects that keep time, precise, regular, clockwork time, that the physics says they should not be able to keep at all. Number 8. The objects that keep the wrong time. A pulsar is one of the most reliable machines in the universe. It is a neutron star, the collapsed core of a large star that has already died, spinning rapidly and sweeping a narrow beam of radio emission across space like a lighthouse. If the beam happens to cross the Earth, we record a pulse. The fastest known pulsars rotate about 700 times per second. The slowest ordinary radio pulsars take a few seconds per turn. And that slow end is not an accident of what we have happened to find. It is a boundary predicted by the physics. The boundary is called the death line, and the reasoning behind it is straightforward. A pulsar's radio emission is powered by rotation. The spinning magnetic field generates an enormous electric field near the star's surface, strong enough to tear charged particles free and accelerate them. And those particles then produce a cascade of electron-positron pairs which radiate. Slow the rotation down, and the induced electric field weakens. Below a certain rate, the cascade cannot sustain itself, the particle supply dries up, and the radio emission stops. The star is still there, still spinning, still magnetized. It has simply gone quiet. For 50 years, every radio pulsar ever catalogued sat on the correct side of that line. The theory and the observations agreed, which in astrophysics is rare enough to be worth celebrating. Since 2022, a small and growing set of objects has been found sitting far on the wrong side of it. They are called long-period radio transients, usually shortened to LPTs, and they emit bright, highly polarized, coherent radio pulses on periods measured not in seconds, but in tens of minutes. They are, by the accepted physics, several thousand times too slow to be doing what they are observably doing. Start with the first one, because the story of how it was found is as instructive as the object itself. In the Western Australian desert sits the Murchison Wide-Field Array, which does not look like a telescope at all. There are no dishes. There are 4,096 small metal dipole antennas, arranged in tiles, standing in the red dirt like a field of low metal spiders. Nothing turns. Nothing moves. The array is steered electronically by adjusting the timing with which signals from different antennas are combined, and it observes at low radio frequencies where the sky is bright and messy. It has been running for years, and its data sits in an archive. Tyrone O'Doherty was an undergraduate student at Curtin University. He was working through archival Murchison data using a search technique built to look for exactly the kind of signal that standard pulsar searches are designed to throw away: slow, transient, irregular in appearance. Standard pulsar searches use algorithms tuned for periods between milliseconds and seconds. Anything with a cycle measured in minutes does not look like an astronomical source to that software. It looks like an instrumental glitch, and it is discarded automatically at a stage before any human ever sees it. He found an object that pulsed every 18.18 minutes. It is night in the Murchison. The array is a field of metal in the dark, and nothing about it suggests activity. No motor noise, no moving dish, no light. Above it, the low-frequency sky is awash of galactic emission, the diffuse radio glow of our own galaxy's magnetic field, and against that background, almost nothing stands out. Then, for somewhere between 30 and 60 seconds, one point in that sky becomes one of the brightest radio sources anywhere overhead. The antennas record it without any change in their behavior, because they are not pointed at it and cannot be. They record everything above them at once. The pulse ends. The sky returns to its wash. 18 minutes and 11 seconds later, it happens again. It has been happening at that interval for as long as anything has been listening, and for 3 months in early 2018, the array wrote every occurrence to disk, where it sat, unexamined, until a student ran an unfashionable search across it 4 years later. The object is catalogued as Gleam XJ16275.5-523504, and in practice, everyone calls it Gleam XJ1627. Its pulses lasted between 30 and 60 seconds each, so it spent about 5% of every cycle visible. At peak, it reached roughly 45 Janskis at 154 MHz, which is an extraordinary brightness for a transient of any kind. It was detectable from January to March of 2018, and then it stopped, and it has not returned. Natasha Hurley-Walker, who led the team that published it, described the object in plain language as something that should not exist. That is not marketing. Under the accepted emission physics, an isolated neutron star rotating once every 18 minutes should be radio silent, permanently. The detail worth holding on to is how ordinary the circumstances were. There was no new telescope, no new mission, no funding announcement. There was an archive that already existed, a student who had been given a project, and a search that deliberately kept the data everyone else's software was written to delete. The result was a new category of astrophysical object. Whole careers are built on incremental refinements of known things. This was a first-year problem that produced a phylum. And the object had been sitting in the archive, in a public dataset, doing exactly this the entire time. That phrase is worth keeping, because it will return later on this list in a much harder form. It was in the data the whole time. The second object made the point unavoidable. GPM-J 1839-10 was announced in 2023, with a period of about 21 to 22 minutes. When the team went back through archival observations from multiple independent radio telescopes, they found it again and again and again, detections stretching back roughly 33 years to 1988. This object has been pulsing on that clock through the entire modern era of radio astronomy. It was above the horizon during essentially every major survey of the last 3 decades. Nobody ever wrote it down, because the software was not built to see it, and because a signal that appears once every 21 minutes does not look like anything a catalog has a column for. The third object added a wavelength. ASCAP J 1832-0911, reported in 2025, has a period of 44.2 minutes, and it is the first, and so far only long-period transient, detected simultaneously in radio and in X-rays, using ASCAP together with the Chandra X-ray Observatory. That matters enormously, because X-rays tie the pulses to a hot, compact object, rather than to some diffuse process spread across a large volume. Something small and hot is doing this. A fourth, ASCAP J 1935 plus 2148, has a period of about 54 minutes and switches between 3 distinct emission states: bright pulses, weak pulses, and nothing at all. And a fifth, ILT J 1101 plus 5521, reported in 2025 from LOFAR data in Europe, was traced to a binary system containing a white dwarf and a small red dwarf companion. That last one is the most informative of all, because it demonstrates that at least some members of this class are not neutron stars. It is worth being precise about what coherent means here, because it is the property that makes these objects a problem rather than a curiosity. Thermal radiation, the glow of anything hot, is incoherent. Its brightness is capped by temperature, and to be as bright as these pulses, a thermal source would need a temperature of something like 10 to the 30th Kelvin, which is not a physical possibility. Coherent emission is different. It happens when enormous numbers of charged particles radiate in step, like a laser rather than a light bulb, and the brightness scales not with the number of particles, but with the square of it. Only a few processes in nature are known to do this, and all of them require a highly organized magnetic environment and a continuous supply of freshly accelerated particles. Pulsars manage it. Fast radio bursts manage it. Nothing rotating once every 44 minutes was supposed to manage it. The pulses are also strongly linearly polarized, in some cases close to completely. Polarization is a direct readout of magnetic field geometry, and a high linear polarization fraction means the emitting region sits in a field that is ordered rather than tangled. That is another pulsar-like signature, and another reason the community took these objects seriously immediately rather than assuming interference. And the timing is exact. GPM J 1839-10's period is stable to a precision that allows detections separated by decades to be phase-connected. That is, you can predict where in the cycle a pulse should fall in 1993 from measurements made in 2023, and it lands where predicted. Whatever is doing this is a rotating or orbiting body with a moment of inertia large enough that nothing has measurably slowed it in 3 decades. That single fact rules out a large number of otherwise appealing models, because most energy-releasing processes leave a signature in the spin-down rate, and here there is essentially none to find. So what are they? There are 3 serious candidates, and no consensus. The first is an ultra-long period magnetar. Magnetars are neutron stars with magnetic fields 1,000 times stronger than ordinary pulsars, and they are powered not by rotation, but by the slow decay of that field. A magnetar could, in principle, keep emitting long after crossing the death line, because rotation is not its energy source. The difficulty is that magnetar fields decay, and an object still active after millions of years of spin-down is hard to arrange. The second is a white dwarf pulsar. A white dwarf is roughly the size of the Earth, where a neutron star is roughly the size of a city, and that difference in size is exactly why their natural rotation periods differ by a factor of thousands. A white dwarf rotating once every 20 minutes is entirely unremarkable. The problem has always been whether a white dwarf can generate the required electric fields at all, and the ILT J1101 binary identification suggests that at least in some configurations it can. The third is that the period we measure is not a rotation at all, but an orbit, two objects circling each other, with the radio emission produced by their interaction, switching on once per revolution. There are also stranger proposals. A 2025 paper argued that some of the isolated sources are strange dwarf pulsars, compact objects with a core of strange quark matter beneath a crust of ordinary matter, a hybrid that would have exactly the size and moment of inertia needed. That model has been applied to Gleam XJ1627, GPM J1839-10, ASCAP J1832-0911, and one other. A comprehensive review of the whole class appeared in January of 2026. Its conclusion, stated in the careful language of reviews, is that this is almost certainly not one kind of object. There is one further observation that deepens the puzzle, rather than resolving it. Several of these objects switch off. Gleam XJ1627 ran for 3 months and stopped. ASCAP J1935 plus 2148 cycles between a bright state, a weak state, and complete silence. GPM J1839-10 has active windows and quiet windows spread across its 3 decades of archival detections. Intermittency is known in ordinary pulsars. There is a class of them called rotating radio transients that flicker in and out, but the timescales here are different, and no accepted model explains why a source of this kind would run for a season and then stop for years. That intermittency also corrupts every attempt to estimate the population. A survey that observed the right patch of sky at the right sensitivity would still have found nothing if the object happened to be in a quiet phase, and there is no way to know how many quiet objects were passed over. The honest summary is that we have discovered a class of source whose members are individually inexplicable, whose collective number is unknown, whose duty cycle is unknown, and at least one of which we can prove has been operating continuously since before the World Wide Web existed. Now the hypothetical, and it is labeled as speculation because that is what it is. Suppose long-period transients are not rare. Suppose they are common and simply invisible to conventional searches by construction. The known population went from 0 to roughly a dozen in 4 years, which is the shape of a discovery curve at the beginning rather than the end. Every one was found by someone deliberately switching off a filter. If the sky contains a large population of slowly beating objects, then the radio surveys of the last 50 years have been systematically discarding them, in real time, as noise, not through incompetence, but because the definition of signal was written before the objects were known to exist. There is a practical footnote that makes the archival story worse rather than better. Radio survey data is enormous. A single night of observing with a wide-field low-frequency array produces volumes of data that cannot be stored in raw form indefinitely, so most of it is reduced on the fly, averaged in time, averaged in frequency, thresholded, and written out as a catalogue of detections rather than as a recording of the sky. The averaging is the problem. A pulse lasting 40 seconds inside an 18-minute cycle disappears completely if the data is averaged over 10 minutes, because the signal is diluted below the noise. Any object of this class observed by a survey that averaged aggressively was not merely unrecognized. Its evidence was destroyed at the point of processing, permanently, and no reanalysis can recover it. which means the count of long-period transients we have is not a census. It is a record of the small subset of cases where the observing mode happened to preserve the signal and somebody happened to look. There is no way to estimate from that what the true population is, other than to say it is larger, possibly much larger, than a dozen. The square kilometre array, whose low-frequency component is being built in the same Western Australian desert, will be the first instrument designed with this class of object in mind, and it will be the first honest measurement of how many of them the galaxy contains. That is the genuinely uncomfortable part of this entry, and it is not really about neutron stars. The discovery here is not an object. It is a demonstration that our instruments have a shape, that the shape was decided by what we expected to find, and that at least one entire category of astrophysical source spent 5 decades falling through the gap between the expectation and the sky. Those objects were hidden by the way we listen, and the way we listen can be changed. The next entry was impossible to miss. It arrived on an ordinary Sunday in 2022, and it briefly overwhelmed almost every instrument ever built to measure that kind of event. Number 7. The brightest thing we have ever seen. On the 9th of October 2022, a signal arrived at Earth that was so bright it broke the instruments built to measure it. The event was catalogued as GRB 221009A, following the convention that encodes the date directly into the name. Within days, it had acquired a nickname, and the nickname was not cautious. Astronomers began calling it the Boat, standing for brightest of all time. Nicknames of that kind usually do not survive contact with careful analysis. This one did. A detailed study published in 2023 by Eric Burns, Dmitry Svinkin, and a large collaboration established that GRB 221009A is the brightest gamma-ray burst ever detected by the two measures that matter: peak flux, which is how bright it was at its brightest instant, and fluence, which is the total energy delivered over the whole event. Their phrasing about rarity is worth quoting carefully, because it is more interesting than the headline. By geometric extrapolation of the known distributions of burst brightness, GRB 221009A appears to be a once-in-10,000 years event. It is therefore almost certainly not the brightest gamma-ray burst in the history of the universe. What it plausibly is, in their words, is the brightest gamma-ray burst since human civilization began. To understand why that matters, it helps to know what a gamma-ray burst is. When a star of more than roughly 20 solar masses exhausts its fuel, its core collapses. In most cases, the result is a supernova and a neutron star or a black hole. In a small fraction of cases, the collapsing core is rotating fast enough that the infalling material forms a disk, and the system launches 2 narrow jets of matter along the rotation axis at very nearly the speed of light. Those jets punch out through the star's outer layers, and where they emerge, they radiate gamma rays. The energies involved are the largest released by any single event in the universe after the beginning itself. Because the jets are narrow, we only see a burst if one of them happens to be pointed at us. That geometry is the key to this entire entry. The detection itself is worth describing, because the way instruments failed is part of the record. GRB 221009A was seen by Fermi, by Swift, by Conus Wind, by Integral, and by dozens of other spacecraft and ground stations. Several of them could not measure it properly. Detectors of this type work by counting individual photon arrivals, and when photons arrive faster than the electronics can process them, separate events are recorded as one, an effect called pile-up. The instruments did not fail in the sense of stopping. They failed in the sense of underreporting, and every published brightness figure required a correction for saturation before it could be trusted. Fermi's gamma-ray burst monitor, which has recorded thousands of bursts without difficulty, was effectively blinded for the brightest part of the event. For scale within its own category, the previous holder of the informal title was GRB 130427A in 2013, which was itself described at the time as extraordinary. GRB 221009A delivered roughly 70 times its fluence. Bursts are usually compared on a logarithmic scale because they span such an enormous range. This one sat off the end of the plot, in a region the distribution had never been tested in. It is also unusually nearby. The median redshift for long gamma-ray bursts is somewhere around 2, meaning most of them come from a time when the universe was less than a third of its present age. Redshift 0.151 is, by that standard, practically local. There is no shortage of intrinsically brighter bursts in the catalogue. There is a shortage of bright bursts this close, aimed this precisely, and that combination is what the once-in-10,000 years figure is measuring. The rarity is not in the explosion. It is in the geometry. Now the numbers. The burst originated in a galaxy at a redshift of 0.151, which places it about 2 billion light-years away, in the small constellation Sagitta. It has the highest isotropic equivalent total energy ever measured for a gamma-ray burst. That quantity is a bookkeeping convention. It is the energy the event would have released if it had radiated equally in every direction, which for a jetted source is a significant overestimate. But it is a standardized overestimate, applied identically to every burst, which makes the comparison fair. Here is the peculiar part. Its peak luminosity sits at roughly the 99th percentile of the known distribution. Not the highest. Not close to the highest. It is a very luminous burst, but there are bursts we have seen that were intrinsically more luminous. What made this one incomparable was not that it was the most powerful. It was that it was unusually close, and that its narrow jet was aimed with remarkable precision at us. We were looking straight down the barrel. The favored structural model, worked out over the following 2 years, describes a narrow inner jet dominated by magnetic energy, what physicists call pointing flux dominated, surrounded by a broader wing dominated by ordinary matter. The extreme brightness comes from the alignment of that narrow core with our line of sight. That is a satisfying explanation for why it looked the way it did, and it explains nothing about the 2 things on this list that remain genuinely unexplained. The first is the photons. The Large High-Altitude Air Shower Observatory sits at 4,410 meters of altitude in the mountains of Sichuan, in China. It does not detect gamma rays directly. It detects the showers of secondary particles those gamma rays create when they hit the top of the atmosphere, which is the only practical way to catch photons at the highest energies, because there are too few of them for a satellite detector to collect. From GRB 221009A, that observatory recorded more than 5,000 very high-energy photons, and the most energetic of them carried about 18 tera-electron volts. 18 tera-electron volts from a source 2 billion light-years away was not supposed to arrive. The reason is a process that has been well understood for 60 years. The universe between the galaxies is not empty of light. It contains the extragalactic background light, the accumulated glow of every star that has ever shone, spread thinly across intergalactic space, mostly in the optical and infrared. A gamma ray traveling through that field can collide with one of those low-energy photons, and if the combined energy is sufficient, the 2 photons convert into an electron and a positron. The gamma ray is gone. The probability of this happening rises steeply with the gamma ray's energy, and above about 10 tera-electron volts, the universe becomes effectively opaque over intergalactic distances. Over 2 billion light-years, the expected survival probability for an 18 tera-electron volt photon is very small. Not zero. The calculation depends on the density of the background light, which is genuinely uncertain at the tens of percent level, but small enough that 5,000 very high-energy photons, with the top of the distribution reaching that far, is difficult to accommodate. The explanations under discussion fall into two camps. The conservative camp says the extragalactic background light is thinner than the models assume, which would push the opacity down and let more photons through. That is possible, and it is the kind of correction that gets made routinely, but the required adjustment is uncomfortably large. The other camp says the photons are not behaving like ordinary photons over that distance. The most discussed candidate is an axion-like particle, a hypothetical very light particle that a photon can convert into in a magnetic field and convert back from later. A photon that spends part of its journey as an axion-like particle is not subject to pair production during that stretch, and effectively travels further than it should be able to. Another proposal involves Lorentz invariance violation, the idea that the relationship between energy and momentum changes very slightly at extreme energies, shifting the threshold for pair production. A paper published in late 2025 asked the question directly in its title, whether there is new physics beyond 30 tera-electron volts in this burst. None of it is resolved. What is not in dispute is the measurement. The second unexplained thing is what the star left behind. Long gamma-ray bursts come from collapsing massive stars, and collapsing massive stars produce supernovae. In the great majority of well-observed long bursts, a supernova appears in the following weeks, brightening as radioactive nickel decays, and it is detected as a characteristic bump in the fading afterglow. For the most energetic burst in recorded history, the natural expectation was a correspondingly impressive supernova. Searches found, at best, a faint and ambiguous signature. Nothing like the record scale of the burst itself. The most energetic explosion we have ever observed appears to have been accompanied by an unremarkable supernova, or possibly by no visible supernova at all. There are ways to arrange this. If most of the star's energy went into the jet rather than into blowing off the envelope, the visible explosion can be modest, but it means the relationship between the jet and the star is not what the standard picture describes. Then there is the effect that brought the event down to ground level. Radiation from the burst reached the upper atmosphere of the Earth and measurably changed it. Instruments in Europe and India recorded a sudden increase in ionization in the lower ionosphere at altitudes of 60 to 90 kilometers. Very low-frequency radio signals, which travel long distances by bouncing off the underside of the ionosphere, shifted in amplitude and phase for the duration and for some time afterward. That kind of disturbance is routine after a solar flare, because the Sun is 150 million kilometers away. This one was produced by an explosion 2 billion light-years away, and it is the first time a gamma-ray burst has been shown to alter the Earth's ionosphere from cosmological distance. There is a related detail that turned the burst into an instrument. The Swift satellite's X-ray telescope recorded a set of expanding concentric rings around the burst position in the days that followed. Those rings were not part of the explosion. They were the burst's own X-rays, scattered off dust clouds within our own galaxy at different distances, arriving late by different amounts. By measuring the ring radii and their expansion rates, astronomers reconstructed the three-dimensional positions of about 20 separate dust layers between here and Sagitta. A single event, 2 billion light-years away, was used to map the interstellar medium of the Milky Way. The follow-up campaign continued for the better part of 2 years, and the search for the supernova is a useful illustration of how these things are actually done. A gamma-ray burst afterglow fades along a predictable power law as the jet decelerates into the surrounding gas. If a supernova is present, its light adds a bump on top of that decline, peaking a few weeks after the burst and colored red by the physics of radioactive decay. Astronomers therefore fit the smooth afterglow, subtract it, and look at what is left. For this event, the subtraction was made difficult by an unusually bright host galaxy, along the same line of sight, and by heavy dust extinction in our own galactic plane, which sits directly in the way. The residual was small, uncertain, and consistent with either a modest supernova or none. That ambiguity has not been resolved. The internal structure of the burst has kept generating results as well. The prompt emission was not a single pulse, but a complex sequence lasting hundreds of seconds, and a 2026 analysis focused on the single brightest flare within it, a flare which, taken on its own and placed at a typical distance, would have been catalogued as a bright gamma-ray burst in its own right. The event contains multiple ordinary bursts nested inside an extraordinary one. One last comparison makes the energy scale concrete without abstraction. The Sun radiates a certain amount of energy every second, and over its entire 10 billion-year lifetime, it will radiate a total that is fixed and calculable. The isotropic equivalent energy released by GRB 221009A in a few hundred seconds is on the order of 1,000 times what the Sun will emit across its whole existence. The true energy, corrected for the narrowness of the jet, is far less than that, perhaps a 10,000th of it, but even the corrected figure is comparable to converting several times the mass of the Earth entirely into light. There is a coda to the dust ring measurement that is worth keeping. Those rings were visible for weeks, expanding steadily outward from the burst position, and each one corresponded to a specific cloud of dust at a specific distance inside our own galaxy. The geometry is simple. X-rays that scattered off a nearer cloud took a shorter detour and arrived earlier. X-rays that scattered off a more distant cloud took a longer detour and arrived later. Measure the timing and the angle, and the distance falls out. Nothing about the burst was designed to be useful. It simply happened to be bright enough and close enough and behind enough dust that for a few weeks the Milky Way's interstellar medium was backlit by a dying star 2 billion light-years away. That is the only time it has happened, and there is no reason to expect it again. Now the hypothetical, clearly labeled as speculation. Move GRB 221009A closer. Keep the alignment and the jet geometry and simply reduce the distance from 2 billion light-years to a few thousand, somewhere in our own galaxy, still far enough away that no individual would notice the star. The physics of what happens next is well studied because the question has been asked repeatedly. The gamma rays deposit their energy in the upper atmosphere. Nitrogen and oxygen molecules are broken apart and recombine into nitrogen oxides. Nitrogen oxides are catalytic destroyers of ozone, meaning each molecule can destroy many ozone molecules without being consumed. Modeled ozone depletion from a nearby burst runs to tens of % globally, and it persists for years because the nitrogen oxides take that long to be removed from the stratosphere. The immediate radiation dose at ground level is not the danger. The danger is the ultraviolet that arrives afterward, for a decade, through a damaged shield. That scenario has been proposed as an explanation for the Ordovician extinction about 445 million years ago, which killed a large fraction of marine life and shows a pattern of losses weighted toward organisms living near the ocean surface. It has never been demonstrated, and it should not be presented as anything more than a hypothesis with a suggestive shape. What GRB 221009A actually supplies, is a calibration. It is a once-per-10,000-year event seen from 2 billion light-years at an angle that flattered it enormously. And even at that distance, even after 2 billion years of travel, it reached down and rearranged the chemistry of our upper atmosphere for a few hours. Nobody was harmed. Nobody outside the profession noticed. The instruments that recorded it needed their data corrected afterward for pile-up, because the detectors had been overwhelmed by a rate of photons they were never designed to handle. Amateur astronomers detected the afterglow, which for a gamma-ray burst almost never happens. The afterglow remained visible across the spectrum for months, fading slowly until it dropped below every instrument's threshold and the event became a set of files. That was one explosion, once, and by the arithmetic of rarity, we will not see its equal again for a very long time. The next entry on this list is the opposite in every respect. It happens thousands of times a day, in every direction, and it has been happening for as long as anyone has been listening. Number 6. The bursts that cross the universe. In 2007, Duncan Lorimer set a student to work on archival data from the Parkes Radio Telescope in New South Wales, recorded 6 years earlier during a survey of the Magellanic Clouds. The task was routine. What the student found was not. Buried in the recording from the 24th of July, 2001, was a single flash of radio emission lasting less than 5 milliseconds, brighter than anything else in the file, and gone. The community's first reaction was that it was interference. That reaction was reasonable. The Parkes telescope had a long history of picking up terrestrial signals, and a few years later, the same instrument was found to be recording a class of false signal that turned out to be the observatory's microwave oven being opened before its timer finished. For 6 years, the Lorimer burst was treated as a probable artifact. It was not an artifact. There are now thousands of them, and they are one of the strangest ongoing phenomena in astronomy. A fast radio burst is a flash of radio emission lasting typically a few milliseconds, arriving from far outside our galaxy, releasing in that instant an amount of energy comparable to what the sun emits over days. That comparison is worth holding still for a moment. The sun is a star. It has been converting 600 million tons of hydrogen every second for 4.5 billion years. Something out there matches days of that output in 1,000th of a second, and then in most cases never does it again. The instrument that changed the field is called CHIME, the Canadian Hydrogen Intensity Mapping Experiment in British Columbia. Like the Murchison array at number 8, it has no moving parts. It consists of 4 stationary half-pipe reflectors, each about 100 meters long, lying on the ground and pointed permanently at the sky directly overhead. It cannot be aimed. Instead, it observes whatever the rotation of the Earth carries above it, which over the course of a day is a strip covering a large fraction of the northern sky. Its collecting area is roughly 8,000 square meters. CHIME detects, on average, between 2 and 3 fast radio bursts every day. Its second catalogue contains 4,539 bursts. Of those, 981 belong to 83 sources that have been observed to repeat, and 3,558 are apparently one-off events that have never been seen again. Before CHIME began operating in 2018, the total number of known fast radio bursts in the world was a few dozen. Now, the crucial question, which is how we know they come from outside our galaxy at all. The answer is one of the most elegant pieces of measurement in astronomy, and it is called dispersion. Radio waves traveling through ionized gas do not all travel at the same speed. The free electrons in the plasma interact with the wave, and lower frequencies are slowed slightly more than higher frequencies. Over interstellar and intergalactic distances, that tiny difference accumulates. The result is that a burst emitted at all frequencies simultaneously arrives smeared out in time, the high frequencies first, the low frequencies trailing behind, in a smooth curve whose shape is precisely calculable. That curve is a measurement of how many free electrons the signal passed through on its way here. It is called the dispersion measure, and every fast radio burst has one. The Lorimer burst had a dispersion measure of 375 units, roughly 3 times what the entire Milky Way could supply along that direction. Every burst since has told the same story. The signals have traveled through far more plasma than our galaxy contains. They are extragalactic, and the more dispersed a burst is, the further it has come. That last point converted a mystery into a tool. In 2020, using bursts precisely localized by the Australian Square Kilometre Array Pathfinder, astronomers established a relationship between a burst's dispersion measure and its host galaxy's redshift, known as the Marquardt relation. Because the dispersion counts electrons, and electrons trace ordinary matter, that relation weighs the ordinary matter of the universe along every sightline a burst travels. And it returned a value in agreement with the number derived from the cosmic microwave background, which no other direct method had managed. A large fraction of the universe's ordinary matter is spread so thinly between galaxies that it emits and absorbs almost nothing. Fast radio bursts found it. So a phenomenon nobody can explain has already been turned into an instrument for solving a different problem. That is not unusual in astronomy, and it is one of the reasons the field cares about these objects as much as it does. The first repeater changed the field a second time. FRB 121102A was found to burst again in 2016, which immediately ruled out any explanation involving the destruction of the source. No cataclysm, no merger, no final collapse, because whatever it was survived to do it again. In 2017, it became the first burst ever localized, traced to a small, faint dwarf galaxy about 3 billion light-years away. And at exactly the same position sat a persistent radio source, a compact, steady emitter that does not switch off between bursts. That combination, a repeating burst inside a low metallicity dwarf galaxy with a persistent radio source alongside it, looked for several years like the template for the whole phenomenon. It was not. Later localizations found bursts in ordinary spirals, in massive quiescent galaxies, in merging groups, and in an ancient globular cluster. The template turned out to be one case. It is also worth stating why these events are difficult in the first place, in terms that do not require a model. The relevant quantity is brightness temperature, the temperature a thermal source would need to be in order to shine that brightly from a region that small. For fast radio bursts, the required brightness temperature comes out around 10 to the 36th Kelvin. There is no physical object at that temperature, and there never has been. The number is not a description of anything hot. It is a proof that the emission cannot be thermal at all, that enormous numbers of charged particles must be radiating in step, coherently, in a magnetic field of extraordinary strength. That is the same conclusion the long-period transients at number 8 forced, arrived at from a completely different direction, and it is one of the few things about fast radio bursts that everybody agrees on. Now, the individual cases, because the population as a whole is less interesting than its outliers. FRB 202-20610A was detected on the 10th of June 2022 by ASCAP in Western Australia. Its dispersion was extreme, and follow-up spectroscopy of the host placed it at a redshift of 1.016. That is a look-back time of roughly 8 billion years. The light left before the sun existed. Its burst energy, around 2 × 10⁻42 ergs, was about 4 times greater than any previously known burst, and it remains the highest confirmed redshift for a localized burst. Hubble Space Telescope imaging of its origin found something unexpected. The burst did not come from a galaxy. It came from a compact group of at least 3 galaxies, apparently in the process of merging, a disturbed interacting system rather than a single object. Whatever produced the burst was living inside a collision. Now hold the timescales together, because this is the part that resists intuition. The burst lasted less than 1,000th of a second. It then traveled for 8 billion years. During that journey, the Earth formed, life began, the entire fossil record played out, and every human being who has ever lived was born and died. The group of galaxies that produced it has spent those 8 billion years finishing its merger, and by now it is presumably a single large elliptical galaxy that looks nothing like the object in the photograph. The photograph is of something that no longer exists. The burst arrives. 3 milliseconds in a receiver in the Western Australian desert, sorted into frequency channels, written to disk. The higher frequencies land first, the lower ones a fraction of a second behind, the delay carrying the imprint of 8 billion years of thin intergalactic plasma. Nothing about the detection is dramatic. There is no alarm, no visible flash, no sound. A pipeline flags a candidate. A human being looks at a plot the following morning. Then there is the case that breaks the model, and it is the closest one. FRB 2020120E was discovered by CHIME and then localized, using the European Velby network, to a globular cluster in the M81 system, only about 12 million light-years away, which for this phenomenon is next door. The localization is precise. The burst sits about 2 parsecs from the optical center of the cluster. That location is a problem, and it is worth being exact about why. The dominant model for fast radio bursts is a young magnetar, a neutron star with an extraordinarily strong magnetic field formed recently in the core collapse supernova of a massive star. Massive stars are short-lived, so magnetars are found in regions of active star formation, spiral arms, starburst galaxies, dwarf galaxies with ongoing starbirth. That is exactly where most well-localized bursts are found. Globular clusters are the opposite. They are dense, ancient, gravitationally bound swarms of hundreds of thousands of stars, and they stopped forming stars billions of years ago. There has not been a core collapse supernova in that cluster since long before the Earth existed. Whatever is producing repeating bursts, there cannot be a young magnetar, because there is nothing young in it. The proposed workarounds involve the specific dynamics of dense clusters, a magnetar formed not from a massive star, but from the merger of 2 white dwarfs, or from a neutron star that accreted enough matter from a companion to collapse. Both are plausible in a globular cluster, where stellar encounters are common. Both require a formation channel different from the one that explains the rest of the population. The M81 source has kept behaving awkwardly since its localization. In 2023, a burst storm was recorded from it, a dense sequence of bursts in a short window, of the kind normally associated with the most active young repeaters. In 2024, a single exceptionally bright burst from the same object was published separately. The source is not a marginal detection producing occasional ambiguous events. It is one of the better studied repeaters in the catalogue, sitting in the one environment where the leading model says it should not be. There is a further wrinkle in the statistics that nobody has resolved. Repeaters and apparent one-offs do not look identical. On average, bursts from repeaters are longer in duration and narrower in frequency than bursts that have never been seen twice. That difference is small but persistent across catalogues, and it admits two readings. Either there are genuinely two populations with two different origins, or there is one population and the apparent one-offs are simply repeaters we have not yet caught a second time, with the observed difference produced by selection effects. Neither reading has been established. The second catalogue's uniform statistics across 80 repeaters was assembled specifically to attack that question, and the honest summary of the result is that the answer depends on assumptions about the burst rate distribution that cannot currently be measured. The magnetar connection is real, though, and it deserves proper credit. In April of 2020, the galactic magnetar SGR 1935 plus 2154 produced a radio burst. It was detected by CHIME and by a small dedicated instrument called STARE-2, and its energy was such that if the same event had occurred in a nearby galaxy, it would have been catalogued without hesitation as a fast radio burst. That is the strongest single piece of evidence that magnetars can make these events, and it arrived 13 years after the Lorimer burst. What it is not is evidence that all fast radio bursts are magnetars. The energy range spanned by the known population covers more than 7 orders of magnitude, a factor of 10 million between the faintest and the brightest. FRB 202-20610A is millions of times more energetic than the galactic magnetar burst. Any single mechanism that has to cover that range is being asked to do a great deal. The population also splits in ways that resist a single explanation. Most bursts are seen once and never again. A minority repeat, and some of those repeat with structure rather than at random. FRB 180916b repeats on a cycle of 16.35 days. It is active for a few days, then silent for the remainder, then active again, and the pattern has held across years of monitoring. A period like that points at an orbit or at the precession of a spinning object, not at a random process. Something is turning the source on and off on a schedule. The recent results have sharpened the picture without settling it. FRB 202-50316A, nicknamed RB Float, was detected in 2025 and localized to a precision of 13 parsecs, about 42 light-years, in a nearby galaxy. That is by a wide margin the most precise localization of a one-off burst ever achieved, precise enough to compare the position against individual stars in the field and to rule out a large number of candidate progenitors directly. In 2025, CHIME reported 30 new repeating sources and uniform population statistics across 80 repeaters. By early 2026, one repeating source, FRB 202-20529A, had been shown to have a steadily declining dispersion measure, direct evidence that its engine sits inside an expanding cloud of material, almost certainly a young supernova remnant thinning out as it grows. In April of 2026, CHIME reported tracking a hyperactive repeater producing bursts at rates the earlier catalogues had no category for. So the field is moving quickly, and the population keeps refusing to be one thing. A few technical details are worth having because they constrain what the source can be. Some bursts are 100% linearly polarized, which implies an extremely ordered magnetic environment at the emission site. Some show a downward drift in frequency across the burst, the so-called sad trombone effect, which suggests emission from progressively further out in a magnetosphere. And the finest structure ever resolved inside a burst is a few tens of nanoseconds long. Light travels about 10 meters in that time, which sets an upper limit on the size of the emitting region. Whatever is producing this energy is doing it in a volume a few meters across. That last constraint is the reason the techno-signature question keeps appearing in the literature, and it deserves an honest answer rather than a dismissal. Here is the honest answer, labeled as speculation on both sides. A fast radio burst is a coherent, extremely powerful, extremely brief radio transient, and coherent radio transients are precisely what a communicating civilization would be expected to produce. That observation has been made in serious journals, and it is not silly. What is also true is that every well-studied burst is consistent with a natural compact object origin, and no burst has ever shown the properties an engineered signal would be expected to show. There is no narrowband carrier. There is no drift correction of the kind a transmitter on a rotating planet would need to apply. There is no information content, no structure that survives analysis as anything other than plasma physics. The most exotic serious proposal in the literature, that bursts could be leakage from light sail propulsion beams, was published as a demonstration of what the numbers would have to look like, not as a claim about what they do look like. What is genuinely unsettling about fast radio bursts is not that they might be artificial. It is the plain arithmetic of the population. Something in the universe releases a sun's worth of days of output in 1,000th of a second. It does this thousands of times per day. It does it in every direction, at every distance out to at least redshift 1, and it has presumably been doing it since the first compact objects formed. We have been able to detect them for 19 years. We have localized a few dozen precisely. And at least one of those localizations sits in a place where the leading model is not merely strained, but excluded. There is one more thing these bursts do, and it belongs to the theme of this list rather than to the physics. Because dispersion counts electrons along the entire path, and because bursts arrive from all distances, they are becoming a survey instrument for the space between galaxies, the least observed volume in the universe, the part that contains most of the ordinary matter and almost none of the light. Chord, Chime's successor, is designed to localize hundreds of bursts per year. Within a decade, the map of intergalactic matter will have been drawn using flashes whose origin nobody can explain. That is a recurring shape in this subject. We keep learning to measure the universe with phenomena we do not understand, and the measurements are excellent, and the phenomena remain exactly as unexplained as they were at the beginning. Those bursts, at least, come from somewhere. Every one has a dispersion measure, a distance, and in the best cases, a host galaxy that can be photographed. The next entry has no source at all, because it is not an object. It is a direction, a preferred axis printed into the oldest light in the universe, pointing, for no reason anyone can explain, uncomfortably close to us. Number 5. The direction the universe should not have. We are halfway down the list, and it is worth stopping to see how far the ground has already shifted. We began with rings 1 million light-years across, around galaxies 2 billion light-years away, made of nothing our instruments can identify except aged electrons in a magnetic field. Then a star close enough to see in binoculars, whose age has been measured 4 times across 4 billion years of disagreement. Then objects in our own galaxy pulsing on clocks the physics forbids, one of them running since 1988 without anyone writing it down. Then a single explosion that changed the chemistry of our upper atmosphere from 2 billion light-years away. Then a population of millisecond flashes arriving thousands of times a day from across the observable universe, at least one of which comes from a place where it cannot come from. Every one of those is an object, or a class of objects, or an event. Each has a location. Each could in principle be pointed at. From here on, that stops being true. The remaining 5 entries are not things. They are properties of the universe as a whole, and the first of them is a direction. The cosmic microwave background is the oldest light in existence. For the first 380,000 years after the beginning, the universe was hot enough that hydrogen could not hold onto its electrons, and free electrons scatter light relentlessly. The universe was opaque, not dark, but foggy, glowing, and impenetrable. Then it cooled below about 3000 Kelvin. Electrons and protons combined into neutral atoms, and the fog cleared in what was, cosmically speaking, an instant. The light released at that moment has been traveling ever since. Stretched by the expansion of space by a factor of about 1100, it now arrives as microwaves at a temperature of 2.725 Kelvin from every direction at once. It is astonishingly smooth. After you remove the dipole, the largest signal, about 1 part in 1,000, which is simply the Doppler effect of our own motion at roughly 370 kilometers per second, what remains varies by about 1 part in 100,000 across the entire sky. That smoothness is the foundation of modern cosmology. It is the observational basis for the cosmological principle, the assumption that the universe is homogeneous and isotropic, the same everywhere and the same in every direction. Nearly every number in cosmology is derived from a model that assumes it. The distance to a galaxy, the age of the universe, the density of dark matter, the expansion rate, all of them are outputs of a framework that begins by asserting that our position and our orientation are not special. The anomaly is that the oldest light appears to contain a direction anyway. Here is how it is measured. A map of temperature across a sphere can be decomposed into patterns of different angular scale, in the same way a sound can be decomposed into frequencies. The largest pattern after the dipole is the quadrupole, which divides the sky into 4 alternating hot and cold regions. Next is the octupole, with 8. In a universe with no preferred direction, the orientations of these 2 patterns should be entirely unrelated to each other and entirely unrelated to anything local. They are not unrelated. The quadrupole and the octupole are aligned with each other, sharing an axis to a degree that random chance makes unlikely. And that shared axis lies close to the plane of the ecliptic, the plane in which the Earth orbits the Sun. The alignment was first noticed in data from the WMAP satellite in the early 2000s, and it was characterized in detail in 2005 by Kate Land and João Magejo, who gave it the name that stuck. They called it the axis of evil. The name is a joke, and a deliberately provocative one, and it has caused endless trouble in popular accounts. What it actually describes is a coincidence between the largest scale structure of light, emitted 13.8 billion years ago, and the orbital plane of one small planet around one ordinary star. Those 2 things have no physical relationship of any kind. The light was emitted more than 9 billion years before the solar system existed. There is no mechanism by which the geometry of Earth's orbit could imprint itself on the primordial sky, and no mechanism by which the primordial sky could have arranged itself around a planet that would not form for billions of years. So there are exactly 3 possibilities, and the field has been arguing among them for over 20 years. The first is chance. There are a finite number of large-scale patterns available, and some coincidence among them is expected. Furthermore, the anomaly was identified after the data was examined, which inflates any naive significance estimate. If you look for unusual features and then calculate how unusual the feature you found is, you will always get an impressive number. This is the standard objection. It is entirely respectable, and it is probably the majority position. The second is contamination. Something in the solar system, or in our own galaxy, is leaking into the map and has not been removed by the cleaning pipelines. Zodiacal dust in the plane of the solar system is the obvious suspect, precisely because it would explain the ecliptic alignment. Multiple independent analyses have looked for this and not found it, but the possibility cannot be closed off entirely because you cannot prove the absence of a foreground you have not modeled. The third is that the universe genuinely has a preferred axis at the largest scales. That would mean the initial conditions of the universe carried a direction, which would require physics operating before or during inflation, and which would undermine the assumption on which the rest of cosmology is built. 3 generations of satellite have not distinguished between them, and here is the problem that makes this entry different from every other on the list. You cannot increase the sample size. There is one microwave sky. Planck, which mapped it between 2009 and 2013 at a resolution of about 5 arc-minutes, extracted essentially all the information the temperature map contains at large angular scales. There is no more temperature data to collect, ever, by anyone. The limit is not technological. It is called cosmic variance, and it means that for the largest patterns, there are only a handful of independent measurements available in principle, because there are only a handful of ways to fit a very large pattern onto a single sphere. The alignment also does not travel alone, and that is what has kept it alive as a serious question rather than a curiosity. There is the low quadrupole. The largest scale temperature variation in the sky is weaker than the standard model predicts, not dramatically, but persistently, in every dataset since COBE measured it in 1992. There is the hemispherical power asymmetry. Split the sky along a particular axis, and one half has systematically more temperature variation than the other. There is a parity asymmetry, a preference for odd patterns over even ones at large scales. And there is the cold spot, an unusually large and unusually cold region in the southern sky, about 5 degrees across and roughly 70 microkelvin below average. The cold spot has a partial explanation. In 2015, Istvan Shapudi and colleagues identified a supervoid in the direction of Eridanus, about 1.8 billion light-years across, sitting in front of it. Light crossing a large underdense region during an era of accelerating expansion loses a small amount of energy, an effect called the integrated Sachs-Wolf effect, which would cool the light passing through. The void is real. The cooling it produces accounts for part of the temperature deficit and not all of it. Individually, each of these anomalies has a probability of arising by chance somewhere between a few percent and a fraction of a percent. That is unimpressive on its own, and any one of them alone would be filed under coincidence without further comment. The interesting work has been in assessing them together. A study published in 2023 by Jones and colleagues examined the alignment jointly with the hemispherical and parity asymmetries, treating the suite as a single hypothesis rather than a collection of separate curiosities. The combined tension they reported with the standard cosmological model was 5.4 standard deviations. 5 sigma is the threshold at which particle physicists declare a discovery. This is not a discovery, because the anomalies were partly selected after the fact, and the statistical treatment of that selection is genuinely contested. But it is not nothing either, and it has not gone away with better data. Now the newer and stranger measurement, which most people have never heard of. The microwave background is polarized. When the last scattering happened, the light picked up a preferred orientation of its electric field in a pattern that carries its own information. And there is a class of theory in which that polarization should slowly rotate during the journey. The idea is this. If the universe contains a very light field that couples to electromagnetism in a way that treats left-handed and right-handed light differently, a parity-violating coupling, then the plane of polarization of light passing through it will turn, a little, continuously, for as long as the light travels. An axion-like field is the standard candidate. Dark energy is a candidate host for such a field. The total rotation angle, accumulated over 13.8 billion years, is called beta, and measuring it would be direct evidence that the vacuum of space is not symmetric between left and right. The measurement had always been impossible for a boring reason. If your detector's polarization angle is miscalibrated by even a fraction of a degree, you get exactly the same signal, and the calibration uncertainty was always larger than the effect being sought. In 2020, Yuto Minami and Eiichiro Komatsu published a method for separating the two, using the fact that emission from our own galaxy's dust, which is nearby and cannot have rotated much, provides an internal reference against which the more distant microwave background can be compared. Applied to Planck data, the method returned a rotation of roughly 0.35 degrees at about 3 standard deviations. Later work combining WMAP and Planck data sharpened it further without settling it. 0.35 degrees is a very small angle. It is about the apparent width of the full moon divided by 2. The systematics remain brutal, and nobody in the field is calling this a detection. But if it is real, it means that something has been quietly turning the polarization of every photon in the universe for the entire history of the universe, and that the vacuum has a handedness. A satellite called Lightbird, designed in part to settle exactly this question, is in development. There is one more coincidence buried in the birefringence result that is worth surfacing, because it connects this entry to the last one on the list. For a field to rotate light's polarization by a fraction of a degree over the age of the universe, it has to be extraordinarily light, a mass around 10 to the minus 33rd electron volts. That is not a number chosen for convenience. It falls out of the measurement. And it happens to sit at the same order of magnitude as the energy scale associated with dark energy, which is the subject of number 1 on this list. That may be nothing. 2 very small numbers being similar is not an argument, and the history of physics is full of numerical coincidences that dissolved on closer inspection. But it is the kind of coincidence theorists take seriously, because a field that light cannot be an ordinary particle in any conventional sense. It would be spread smoothly across the entire universe, essentially motionless, its energy density nearly constant everywhere, which is a description of dark energy written in different vocabulary. If cosmic birefringence is real, the most economical interpretation is that the thing rotating the light and the thing accelerating the expansion are the same thing, observed 2 different ways. Nobody is claiming that. The measurement is at 3 standard deviations, the systematics are unresolved, and a single miscalibrated detector would produce an identical signal. But it is on the table, it is testable, and a satellite is being built to test it. That makes it one of the few items on this list where the situation may genuinely change within a working career. 2 details make the coincidence at the heart of this entry harder to dismiss than it first appears. The first is geometry. The ecliptic plane is tilted about 60 degrees to the plane of our galaxy. That matters because the galaxy is the dominant foreground contaminant in every microwave map, and every cleaning pipeline is built to remove it. An alignment with the galactic plane would be immediately suspicious and immediately explicable. An alignment with the ecliptic is neither. It is not where the known contamination is. The second is persistence. COBE measured the sky in 1992 at about 7 degrees resolution. WFUMAP measured it from 2003 at about 0.2 degrees. Planck measured it at about 5 arc minutes, with completely different detector technology, a different scan strategy, a different orbit, and a different team. Instrumental artifacts do not usually survive that. The alignment did. Now the hypothetical, and it should be labeled clearly as speculation, because there is no accepted physics behind it. Suppose the third possibility is the correct one, and the universe genuinely has a preferred axis at the largest scales. What would that require? It would require the initial conditions of the universe to have been anisotropic, to have contained a direction, and for inflation to have failed to erase it. Inflation, the brief period of exponential expansion in the first fraction of a second, is supposed to smooth away exactly this kind of feature. A surviving axis would mean either that inflation was shorter than assumed, leaving pre-inflationary structure imprinted on the largest scales we can see, or that whatever preceded inflation had a geometry we have not accounted for. That is not a small correction. Every distance in cosmology, every age, every density, is derived from a model that assumes isotropy. If the universe has a direction, those numbers are not wrong by a rounding error. They are answers to a slightly different question than the one being asked. And there is a version of this that is simply uncomfortable rather than technical. Modern cosmology begins, historically and philosophically, with the removal of Earth from the center of things. Copernicus moved us off the center of the solar system. Shapley moved the sun off the center of the galaxy. Hubble moved the galaxy into a crowd of billions. The cosmological principle is the final step in that sequence, and it is checked against a single map that cannot be remeasured, a map with an axis in it that lies uncomfortably close to the plane in which our own planet moves. The most likely explanation remains chance. That is the honest position, and it is worth saying plainly rather than burying. But the anomaly is 25 years old. It has survived 3 satellites, and no further temperature data will ever be collected to settle it. That is a pattern in light, spread across the whole sky, and it is at least the kind of thing you can argue about statistically. The next entry is a single particle. It arrived at the top of our atmosphere, carrying more energy than any particle should be able to carry over cosmic distances, from a direction in which there is nothing capable of producing it. Number 4. The messengers with no source. Cosmic rays are not rays. The name is a 19th century mistake that stuck. They are particles, mostly bare protons, some heavier atomic nuclei, arriving at the Earth from space at speeds close to that of light. Most of them are unremarkable. The Sun produces a continuous low-energy stream. Supernova remnants within our own galaxy accelerate particles to higher energies through shock waves, and those account for the great majority of what reaches us. Then, at the very top of the energy spectrum, there is a handful of events that have no accepted explanation, and the reason they have no accepted explanation is not that we lack ideas. It is that the physics forbids the only ideas that would work. On the 15th of October 1991, a detector in the Utah desert called Fly's Eye recorded a particle carrying about 320 exa-electron volts. It was named the "Oh my God" particle, in the tradition of physicists naming things badly, and for 3 decades it was the most energetic particle ever detected. On the 27th of May 2021, a much larger instrument in the same desert, the telescope array, recorded a second one. It was announced in November of 2023 and named Amaterasu, after the sun goddess of Japanese mythology, in recognition of the Japanese-American collaboration that built the array. Its energy was about 244 exa-electron volts. Numbers at that scale mean nothing without a comparison. So here is the comparison that physicists use, because it is the one that lands. 244 exa-electron volts is roughly the kinetic energy of a baseball thrown at about 95 kilometers per hour. Not a metaphorical baseball. An actual baseball, thrown by an adult at ordinary speed, All of that energy carried by a single subatomic particle. A proton at that energy is traveling at a speed that differs from the speed of light by about 1 part in 10 to the 23rd. From the particle's own frame of reference, the journey across intergalactic space takes almost no time at all. It carries tens of millions of times more energy than the Large Hadron Collider, a machine 27 kilometers in circumference, cooled to 1.9 Kelvin, consuming the electricity of a small city, manages to give a single proton. Something in the universe is doing this by accident. Now the problem, and it is a hard one, because it rests on physics that has been checked directly. In 1966, Kenneth Greisen at Cornell, and independently Georgy Zatsepin and Vadim Kuzmin in Moscow, worked out what happens to a very high-energy proton traveling through the cosmic microwave background. Space is not empty of light. It is filled with those microwave photons, about 410 million of them in every cubic meter. To a proton moving at nearly the speed of light, a microwave photon coming the other way is blue-shifted enormously. It looks like a gamma ray. And above a certain proton energy, roughly 50 exaelectron volts, that collision has enough energy to create a pion. Creating a pion costs energy, and the energy comes out of the proton. The consequence is a horizon. A proton above the threshold loses energy steadily as it travels, and no matter how energetic it starts, after a certain distance, it has been ground down below the threshold. The practical limit is that a particle arriving here at 244 exaelectron volts cannot have started its journey more than roughly 160 to 300 million light-years away. That is a small volume by cosmological standards. It contains our local group, the Virgo cluster, and a modest number of other structures, all of them mapped. There is a second consequence, and it is the useful one. Charged particles are deflected by magnetic fields, which is why ordinary cosmic rays arrive from random directions and carry no information about where they came from. But the deflection depends inversely on energy, and at 244 exaelectron volts, the deflection by galactic and intergalactic fields is small. A particle at that energy is very nearly an arrow. It is the one cosmic messenger, apart from light and neutrinos, that points back at its source. So, we have a particle that must have come from within about 300 million light-years, and which points at where it came from. Amaterasu points at the local void. The local void is a large and conspicuously empty region of space bordering our own galaxy group. It has been mapped. It contains no active galactic nucleus, no cluster of galaxies, no radio galaxy, no gamma-ray burst remnant, nothing that any known mechanism could use to accelerate a proton to that energy. Trace the trajectory back, allow for every reasonable estimate of magnetic deflection, and the region of sky it emerges from is a hole. The Oh My God particle had a version of the same problem 3 decades earlier, and so do a number of the other highest energy events on record. This is not a single anomalous detection. It is a pattern in a very small sample. Consider what the detection itself actually looks like, because the disproportion is the point. It is late May in 2021 over the Utah desert, and one particle reaches the top of the atmosphere. It strikes a nitrogen nucleus about 20 kilometers up. That collision produces a spray of secondary particles, each of which collides again and again in a cascade that doubles and doubles as it descends. By the time the front of that cascade reaches the ground, it contains billions of particles, spread across a disk several kilometers wide, moving downward at essentially the speed of light. The air along its path fluoresces faintly in ultraviolet as the nitrogen is excited and relaxes. On the desert floor, 507 plastic scintillation detectors sit on a grid spaced 1.2 kilometers apart, covering about 700 square kilometers. 23 of them register the front as it passes. The whole event, from the first collision to the last detector, lasts a few tens of microseconds. Nothing is visible to anyone standing there. The desert is dark and quiet, and one particle has become a sheet of light kilometers across. Then hold the two facts together. The energy of a thrown baseball in one proton, and an arrow pointing back at a part of the sky where the maps show nothing at all. That is where a phrase from the beginning of this list returns, and it returns much harder than it left. The universe does not owe us a source. At number 10, it was an inconvenience about imaging depth. The rings had no counterpart because we could not see faintly enough at other wavelengths, and better instruments would probably fix it. Here, it is not an inconvenience. It is a statement about physics. The particle cannot have come from far away, because the microwave background would have eaten its energy. And there is nothing near enough to have made it. It is worth asking what could accelerate a particle that far in the first place, because the answer narrows the field dramatically. There is a simple constraint, named after Michael Hillis, which says that to accelerate a charged particle to a given energy, the acceleration region must be large enough and magnetized enough that the particle's orbit fits inside it. If the particle's gyro radius exceeds the size of the accelerator, it escapes before it can be accelerated further. Apply that constraint at 244 exa-electron volts, and almost everything drops out. Supernova remnants are far too small. Pulsars are too small unless the fields are extreme. What survives is a short list: the jets and lobes of radio galaxies, the accretion regions around the most massive black holes, gamma-ray burst engines, and the shock fronts of colliding galaxy clusters. All of them are rare, all of them are identifiable, and none of them is in the local void. The composition question compounds this. A proton and an iron nucleus produce air showers that look similar but not identical. The depth in the atmosphere at which the cascade reaches its maximum differs, and so does the number of muons at ground level. Reading composition from that difference requires modeling hadronic interactions at energies far beyond anything a collider can reproduce, which means the models are extrapolations. The telescope array and the Pierre Auger Observatory have historically disagreed about composition at the highest energies, and the disagreement has never been fully resolved. If the highest energy particles are heavy nuclei rather than protons, the arrow argument weakens considerably. If they are protons, it holds, and the problem stands. There is also a large-scale anomaly that sits underneath all of this. Auger has reported a dipole in the arrival directions of cosmic rays above 8 exa-electron volts, a preferred direction in the sky, at a level of about 6%, pointing away from the galactic center and roughly toward the general direction of the nearby extragalactic structure. That is taken as good evidence that the highest energy particles are extragalactic in origin. What it has not done is identify a single source. 2 decades of the largest cosmic ray observatories ever built have produced a statistical direction and no address. The proposals fall into 4 groups, and none of them is comfortable. The first is that we are underestimating the magnetic deflection. Intergalactic magnetic fields are poorly measured, and if they are stronger or more structured than assumed, the arrow is not an arrow, and the true source lies somewhere else in the sky. This is the conservative answer, and it has the disadvantage of requiring fields substantially larger than most estimates allow. The second is that the source has gone quiet. Acceleration to these energies might happen in brief episodes, a jet switching on for a few thousand years and then stopping. The particle takes millions of years to arrive. By the time it gets here, the source has faded. This works, and it is untestable, which is not a virtue. The third is that the particle is not a proton. Heavier nuclei have more charge and are deflected more, which would break the arrow argument entirely, and there is genuine uncertainty about the composition of the highest energy events. A 2024 analysis explored whether super-heavy dark matter decaying somewhere in our galaxy's halo could produce them, which would remove the distance problem completely by removing the distance. And a 2024 paper proposed, seriously if speculatively, that Amaterasu was a magnetic monopole, a hypothetical particle predicted by grand unified theories, never observed, which would interact with the atmosphere in a way that could mimic an extreme energy air shower. The fourth is simply that the local void is not as empty as we think. A paper published in 2026 is titled, "Without any apparent irony, ultra-high-energy cosmic rays from the local void." Now the second messenger, which arrived from a different direction and made everything worse. On the 13th of February 2023, a detector on the floor of the Mediterranean Sea recorded a muon crossing its entire volume horizontally. The detector is KM3NET, and it consists of strings of light sensors anchored to the seabed off the coast of Sicily, 3,500 meters down, watching for the faint blue flashes produced when a neutrino interacts with seawater. At the time of the detection, only a fraction of the planned instrument was installed. The muon carried about 120 peta-electron volts. Working backward to the neutrino that produced it gives a parent energy of roughly 220 peta-electron volts, with a 68% confidence range running from 110 to 790. The event, catalogued as KM3-230213A, was published in Nature in 2025. It is the most energetic neutrino ever observed, by more than a factor of 10 over anything in the entire catalogue of IceCube, the cubic kilometer detector buried in the Antarctic ice. Neutrinos should be the cleanest messengers in astronomy. They carry no charge, so magnetic fields do not bend them. They interact so weakly that nothing absorbs them. A neutrino travels in a perfectly straight line from wherever it was made, across any distance, through anything in the way. If you want to know where a high-energy process is happening in the universe, a neutrino is the ideal witness. The detection principle at KM3NET is worth a sentence, because it explains why the instrument is where it is. A neutrino, on the rare occasions it interacts, converts into a charged particle, for high-energy muon neutrinos, a muon, which then travels through the water faster than light travels through water. That produces a cone of faint blue light called Cherenkov radiation, the optical equivalent of a sonic boom. Detect the timing of that light across a three-dimensional array of sensors and you can reconstruct the direction of the original neutrino to within a fraction of a degree. Seawater at 3.5 kilometers depth is dark, dense, transparent, and free, which is why the detector is on the seabed rather than in a laboratory. The same principle, applied to Antarctic ice rather than Mediterranean water, is what IceCube uses. Both instruments are essentially the same idea, executed in different transparent media, and both have to distinguish genuine cosmic neutrinos from the enormous background of muons produced by ordinary cosmic rays hitting the atmosphere overhead. The trick in both cases is to use the Earth itself as a filter. Look downward, through the planet, and accept only particles that arrived from below, because nothing but a neutrino can cross the Earth. That is why an event crossing the detector horizontally, having traversed 147 kilometers of rock, is such a clean signature. And that is also why the disagreement between the two detectors is so uncomfortable. They are not measuring different things with different techniques. They are running the same experiment in two different places, and one of them has seen something the other should have seen and has not. This one points at a patch of sky with no convincing counterpart. And it creates a second problem, sharper than the first. IceCube is larger than KM3NET and has been running for far longer. If neutrinos at that energy are common enough for a partially built Mediterranean detector to catch one, IceCube should have caught several by now. It has caught none. The statistical tension between the two results has been quantified at between 2 and 3.5 standard deviations, depending on what source population is assumed. Part of the tension may be geometry. The muon crossed KM3NET after passing through about 147 kilometers of rock and seawater, a very different path from what a neutrino arriving at the South Pole would take, and that argument has been made in detail. It reduces the tension. It does not remove it. The proposed origins run the full range. A year-long astrophysical transient. The Blazar PKS 0605-085, which sits near the arrival direction. Cosmogenic neutrinos, produced when ultra-high-energy cosmic rays collide with microwave background photons and create pions, which decay into neutrinos. That last one is elegant, because it would tie the two halves of this entry together. The same interaction that limits how far a proton can travel would be generating the neutrinos, and the neutrino would be the fingerprint of a cosmic ray we never saw. Beyond those, the literature contains proposals involving decaying dark matter of primordial black hole origin, sterile neutrinos, electroweak vacuum turbulence in merging black hole binaries, and processes at the grand unification energy scale. The number of exotic proposals is itself informative. When a single event generates that many papers in that many directions, it means the conventional explanations are not fitting comfortably. Now the hypothetical, labeled as speculation, and it is the reason this entry sits at number 4 rather than lower. If the arrival directions of the highest energy particles genuinely have no sources within the horizon that physics allows, there are only two ways out, and both are uncomfortable in the same way. The first is that the horizon is wrong, that our model of how these particles interact with the microwave background, which is textbook physics confirmed by the observed spectral cutoff in 2007, is incomplete at the extreme end. That would mean the failure is in the part of physics we thought was safest. The second is that the particles are not what we think they are. Not protons, not iron nuclei, not any nucleus, something else, arriving from somewhere the maps show as empty. There is no third option that does not involve someone's measurement being wrong, and the measurements have been checked repeatedly by people motivated to find errors. The rate of these events tells you how thin the evidence necessarily is. Particles above 100 exaelectron volts arrive at roughly 1 per square kilometer per century. The telescope array covers 700 square kilometers. The Pierre Auger Observatory in Argentina covers 3,000. Between them, running continuously for 2 decades, they have collected a sample you could count without running out of fingers and toes. Every one of those events is a single, unrepeatable measurement of something that happened millions of years ago, in a place we cannot identify, by a mechanism we cannot name. Those are single events, and single events can be flukes, however carefully they are measured. The next entry is not an event at all. It is a number, one of the most important numbers in physics, and it has been measured, twice, by 2 of the most careful programs ever run, and the 2 answers cannot both be right. Number 3. The 2 speeds of the universe. The Hubble constant is a single number that describes how fast the universe is expanding right now. It is written as a speed per distance, kilometers per second, per megaparsec. A megaparsec is about 3.26 million light-years. So a value of 70 means that for every megaparsec further away a galaxy sits, it recedes 70 kilometers per second faster. It is not an obscure quantity. It sets the size of the observable universe. It sets the age of the universe. It enters the calculation of the distance to essentially every object beyond our own galaxy, and therefore the calculation of how bright those objects really are, how massive they are, and how long ago they emitted the light we see. It is one of the load-bearing numbers of modern science. There are two independent ways to measure it. They disagree. The disagreement has grown more significant every year for a decade, despite an enormous amount of work by people specifically trying to make it go away. Start with the first method, because it is the older one and because its structure is the reason it is called a ladder. You cannot measure the distance to a distant galaxy directly. What you can do is build a chain of overlapping techniques, each calibrated by the one below it. The bottom rung is geometry, parallax, the tiny apparent shift in a nearby star's position as the Earth moves from one side of its orbit to the other. Parallax requires no assumptions at all. It is trigonometry, and it works out to a few thousand light-years with modern instruments. Within that range there are Cepheid variable stars. A Cepheid pulses, swelling and shrinking on a cycle of days to weeks, brightening and dimming as it does. In 1912, Henrietta Swan Leavitt found that the period of the pulsation is tightly related to the star's true luminosity. The slower the pulse, the brighter the star. That relation is the second rung. Measure a Cepheid's period, read off its true brightness, compare with how bright it appears, and you have its distance. Cepheids are luminous enough to be identified individually in galaxies tens of millions of light-years away. That is far enough to reach galaxies which have also hosted Type 1, a supernovae, the detonation of a white dwarf, which occurs at a characteristic mass and therefore with a characteristic brightness, and which can be standardized further using the fact that brighter ones fade more slowly. That is the third rung, and it is bright enough to be seen across hundreds of millions of light-years, far enough out that the general expansion dominates over the local gravitational motions of galaxies. 3 rungs, each calibrated by the last, reaching from the solar neighborhood to the cosmological flow. This is the distance ladder, and the SH0ES collaboration, led by Adam Rees, has been refining it for 2 decades. Its current value for the Hubble constant is about 73.0, with an uncertainty near 1. A little history makes the current disagreement look smaller and worse at the same time. When Edwin Hubble published the first version of this measurement in 1929, his value was about 500. That is wrong by a factor of 7, and the error was not carelessness. Hubble was using Cepheids without knowing that there are 2 distinct populations of them, with 2 different period luminosity relations. Walter Baade sorted that out in the 1940s, and the value dropped by half immediately. Further corrections followed as astronomers realized that what Hubble had taken for individual bright stars in distant galaxies were sometimes entire star clusters. By the second half of the 20th century, the field had settled into a long and famously bad-tempered argument. Alan Sandage and his collaborators advocated a value near 50. Gérard de Vaucouleurs and his advocated a value near 100. The 2 camps used overlapping data, disagreed about calibration, and did not persuade each other for 30 years. The dispute was so entrenched that many papers simply carried the expansion rate as an undetermined factor rather than committing to a number. That argument was settled, more or less, by the Hubble Space Telescope Key project, which reported a value near 72 in 2001 and was widely treated as closing the question. The uncertainty had come down from a factor of 2 to a few percent, and the discipline moved on. The point of that history is the scale. The 1950s disagreement was a factor of 2. The current one is 9%. By any historical standard, 9% is a triumph of precision. The reason it is a crisis rather than a footnote is precisely that the precision on both sides is now good enough that 9% cannot be absorbed. Two measurements that are each accurate to about 1%, differing by 9, do not average. They contradict. Now the second method, which does not use a ladder at all. Take the pattern of temperature fluctuations in the cosmic microwave background, the same map that produced the anomalies at number 5. Those fluctuations are sound waves. In the hot plasma before recombination, gravity pulled matter into overdense regions, and radiation pressure pushed it back out, and the resulting oscillations were frozen in place at the moment the universe became transparent. The characteristic size of those frozen waves is set by how far a sound wave could travel in the plasma before that moment, a distance called the sound horizon, which works out to roughly 490 million light-years in today's units. That gives you a ruler of known length at a known time. Measure its apparent angular size on the sky, fit the standard 6-parameter cosmological model to the full pattern, and extrapolate forward 13.8 billion years to predict what the expansion rate should be today. The Planck satellite's answer is 67.4, with an uncertainty near 0.5. Measurements of baryon acoustic oscillations from the dark energy spectroscopic instrument, combined with the microwave background, favor something near 68.5, 73.0, and 67.4. The gap is about 9%. The statistical significance is around 5 standard deviations, which corresponds to roughly a 1 in 3.5 million chance that it is a fluctuation. In particle physics, 5 sigma is the threshold at which a discovery is announced. In cosmology, here, it is the threshold at which a contradiction is announced, and the field has been living inside that contradiction since about 2016. Now the part that makes this genuinely difficult, which is how hard people have tried to make it go away. For years, the natural assumption was that something in the distance ladder was wrong. That assumption was sensible. The ladder has 3 rungs, and every rung has potential systematics. The most discussed candidate was crowding. Cepheids in distant galaxies sit inside crowded star fields, and if unresolved neighboring stars leak into the measurement, the Cepheids look brighter than they are, the galaxies look closer than they are, and the inferred expansion rate comes out too high. Dust was the second candidate. Undercorrected extinction would produce a similar bias. The James Webb Space Telescope was the test, and it was a clean one. Its infrared resolution is several times better than Hubble's at the relevant wavelengths, which means it can separate individual Cepheids from their neighbors in galaxies where Hubble could not. If crowding was the answer, JUST would show it immediately. By 2024, the SH0ES team had published JUST-based Cepheid measurements for 8 anchor galaxies that had previously been observed with Hubble. The result was the one nobody in the reconciliation camp wanted. The JUST measurements confirmed the Hubble measurements. They did not revise them downward. Crowding was not the answer, and dust was not the dominant systematic. It is worth standing at the bottom of that ladder for a moment, because the physical reality of it is easy to lose inside the word measurement. A telescope observes a nearby star in January and again in July, 6 months apart, from opposite sides of Earth's orbit. Against the background of much more distant stars, the near one appears to shift by an angle so small that for the nearest stars it amounts to less than 1 arcsecond, and for most useful Cepheids, far less than that. Gaia measures such shifts at the level of micro-arcseconds. The whole edifice above rests on that wobble. From there the chain climbs, a Cepheid in the large Magellanic Cloud, whose distance is independently fixed by detached eclipsing binary stars. A Cepheid in a galaxy 40 million light-years away, resolved from its neighbors only by an instrument in space. A supernova in that same galaxy, calibrated by that Cepheid, and then the same kind of supernova in a galaxy 500 million light-years away, where the expansion of space dominates everything. Each rung is a separate discipline, with its own specialists and its own decades of argument. Nothing about it is a single measurement. It is a structure, built by hand, over a century, and every joint in it has been inspected repeatedly by people hoping to find the loose one. The other anchors deserve naming, because the ladder does not rest on parallax alone. SH0ES uses 3 geometric anchors: the Water Mega-Maser system in the galaxy NGC 4258, where radio emission from a rotating disk around a black hole gives a purely geometric distance; detached eclipsing binaries in the large Magellanic Cloud, where the orbital mechanics give the physical sizes of the stars directly, and parallaxes to Cepheids in the Milky Way. 3 independent geometric foundations. Remove any one of them, and the answer barely moves. Independent methods that bypass Cepheids entirely have also been run. The tip of the red giant branch uses the fact that red giant stars reach a sharp maximum brightness before they change state, giving a standard candle with different systematics. The J-region asymptotic giant branch method uses a different stellar population again. Surface brightness fluctuations use the graininess of an unresolved galaxy's light. Type II supernovae can be modeled spectroscopically to give distances with no ladder at all. Gravitational wave events provide standard sirens, where the waveform itself encodes the distance without reference to any brightness. Time delay cosmography uses gravitationally lensed quasars, where the same variable source arrives along multiple paths with measurable delays. The results from those methods scatter. Some land near 70. Some land closer to 73. A few sit lower. The sample sizes for the newest techniques are small, and no single alternative method is yet precise enough to arbitrate. What has not happened in 10 years of alternative methods is a systematic migration of local measurements down toward 67. So take seriously the possibility that both numbers are correct. If they are, then the standard cosmological model is missing something between the early universe and the late universe. The early universe measurement is not really a measurement of the expansion rate at all. It is a measurement of the sound horizon and the fluctuation pattern, converted into a present-day expansion rate by assuming a particular history in between. Change the history, and the conversion changes. The leading proposals all attack the same target. They shorten the sound horizon by adding something to the universe before recombination. Early dark energy is the most discussed, a component that switches on around the time matter and radiation have equal density, contributes a few % of the energy budget briefly, and then dilutes away. Extra-relativistic species would do something similar. A varying electron mass would shift the recombination epoch itself. Interacting dark radiation is another variant. None of them fits every dataset at once. A survey published in 2021, memorably titled "The H0 Olympics," ranked the proposed models against the full range of available constraints and found no clear winner. Every model that resolved the tension in one dataset created a new tension in another. That situation has not fundamentally changed in the 5 years since. A 2026 analysis went further and dissected the problem using measurements that avoid the sound horizon altogether, specifically to isolate which link in the chain the discrepancy enters through. The alternative to new physics is a local explanation. that we happen to live inside a large, underdense region, a hole in the distribution of matter a few 100 million light-years across. Inside such a region, matter falls outward toward the denser surroundings, adding a small extra recession to nearby galaxies and making the local expansion look faster than the global average. That hypothesis is testable. It has been tested repeatedly, and the evidence for a void large and deep enough to do the job has not held up. There is one more measurement worth naming, because it is the only one that owes nothing to any of the others. In August of 2017, the merger of two neutron stars was detected in gravitational waves and, seconds later, in gamma rays, and then across the entire electromagnetic spectrum as the debris cooled. The gravitational waveform of a merging binary encodes the distance to the source directly, from the amplitude and the way the frequency sweeps upward, with no reference to anything's brightness. Combine that distance with the redshift of the host galaxy, and you get the expansion rate from first principles. Events of that kind are called standard sirens, and they are the only genuinely ladder-free, model-free route to the Hubble constant that exists. The single event in 2017 gave a value of about 70, with an uncertainty of roughly 10, far too broad to arbitrate between 67 and 73. The situation improves as the square root of the number of events, and events with both gravitational and electromagnetic detections remain rare. Estimates for when the siren method reaches the precision needed to settle the question range from a few years to a couple of decades, depending on detector upgrades. That is the position, then. There is a clean, assumption-free method that will eventually answer this, and it is not yet sensitive enough. Everything else on the table is a chain of inference, and the two longest chains disagree. What would it mean if the disagreement is real physics rather than a mistake? Every parameter derived from the microwave background would shift. The inferred density of dark matter would change. The total energy budget would rebalance. The age of the universe would move by hundreds of millions of years in one direction or the other, propagating into every stellar age estimate ever made, including the one at number 9 on this list. And the standard model of cosmology, which is genuinely one of the great achievements of the last century, describing the entire history of the universe with 6 numbers, would need a 7th. Now the phrase from number 8 returns, and it means something harder here. It was in the data the whole time. At number 8, that was a statement about instrumentation, a signal that existed in the archives and was discarded by software written before the object was known to exist. That is a technical failure with a technical fix. Here, the failure is different. The discrepancy between local and early universe expansion measurements was visible in published numbers well before it was accepted as real. For years, it was attributed to underestimated systematics, because the alternative was that a model which had been enormously successful for 2 decades was incomplete. Nobody suppressed anything. Nobody behaved improperly. The measurements were published, and the natural professional response to a small disagreement between a well-established prediction and a difficult measurement is to suspect the difficult measurement. It took the disagreement growing, and independent teams confirming it, and finally a new space telescope failing to make it disappear, before the field accepted that it might be pointing at physics rather than at error. That is a harder problem than a badly written search filter, and it has no technical fix. It is also worth being clear about what the word crisis is doing in this context, because it appears in the titles of review articles, and it is not journalistic exaggeration. In cosmology, a crisis is not a catastrophe. It is a situation in which 2 well-established procedures, applied correctly, produce incompatible answers, and in which no amount of further care within the existing framework is expected to reconcile them. The last comparable episode was the globular cluster age problem of the 1990s, which was resolved by the discovery of dark energy. That is, by adding a component that made up 68% of the universe. Crises of this kind have historically been productive. They are also slow, and they are uncomfortable for the people living through them. And there is a recursion here that ties the two ends of this list together. The age of the universe is not measured directly. It is derived from the expansion history, and the expansion rate is the leading term. A higher Hubble constant implies a younger universe. If the local value of 73 is the correct one, and no new physics intervenes, the universe is closer to 12.8 billion years old than 13.8. Now go back to number 9. The Methuselah star's most recent asteroseismic age is 14.2 billion years, plus or minus 0.4. Against a universe of 13.8 billion years, that is consistent within one standard deviation, and everyone can go home. Against a universe of 12.8 billion years, it is not consistent at all. Neither are the oldest globular clusters, which sit between about 12.5 and 13.5 billion years. The two ends of this list are measuring the same problem from opposite directions. The oldest stars constrain how young the universe can be. The local expansion rate wants it younger. Neither can be resolved without the other, and the resolution, whatever it turns out to be, will move both. That is a disagreement about how fast everything is flying apart, and about how long it has been doing so. The next entry is more fundamental than either. It asks why there is anything flying apart at all, why the universe is made of matter, when everything we know about how matter is produced says it should have been made of nothing. Number 2, the matter that never arrived. Every particle has a mirror image. For the electron, there is the positron, identical in mass, opposite in charge. For the proton, there is the antiproton. For every quark, there is an antiquark. This is not a hypothesis. Antiparticles were predicted by Paul Dirac in 1928 as a consequence of combining quantum mechanics with special relativity, and the positron was found in cosmic ray tracks by Carl Anderson 4 years later. Antimatter is manufactured routinely at CERN. It is used in hospitals. The P in PET scan stands for positron. When a particle meets its antiparticle, they annihilate. Both vanish, and their entire mass converts into energy, usually as gamma rays. This is the only process in nature that is 100% efficient at turning matter into radiation. Nuclear fission converts about 0.1% of the mass involved. Fusion in the Sun converts about 0.7%. Annihilation converts all of it. The annihilation of 1 gram of matter with 1 gram of antimatter would release about 43 kilotons of energy, which is roughly 3 Hiroshima bombs, from 2 objects you could hold in your hands. And here is the fact that creates the problem. Every process that produces matter produces antimatter alongside it, in equal quantity. Put energy into a collision, and you get a particle and its antiparticle out, together, always. That symmetry is not an assumption someone made for convenience. It is measured, repeatedly, in every accelerator experiment ever run, to extraordinary precision. So the universe should not exist. Follow the logic. In the first fraction of a second, the universe was hot enough that particle-antiparticle pairs were being created and annihilated continuously in enormous numbers. As it expanded and cooled, pair creation shut off, and everything that remained should have annihilated with its counterpart. If the production had been exactly symmetric, the end state would have been a universe consisting entirely of photons. No atoms. No stars. No chemistry. No planets, no biology, no observers, nothing but a thinning bath of radiation cooling forever. Instead, something tipped the balance, very slightly. For roughly every billion antiquarks in the early universe, there were about 1,000,000,001 quarks. The billion pairs annihilated as expected. The leftover 1 in a billion is everything that exists. Every galaxy, every star, every planet, every atom in your body, all of it the rounding error of a war that should have ended in a draw. That ratio is not a guess. It is measured 2 independent ways, and they agree. The first is the photon-to-baryon ratio. Every one of those annihilations produced photons, and those photons are still here. They are the cosmic microwave background. Count them, count the protons, and you get roughly 1.6 billion photons for every proton in the universe. That number is the direct fossil of the annihilation. It is a receipt. The second is Big Bang nucleosynthesis. In the first few minutes, protons and neutrons fused into helium, deuterium, and traces of lithium, and how much of each depends sensitively on the density of ordinary matter relative to radiation, the same ratio. Measure the primordial abundance of deuterium in ancient gas clouds, and you get the same answer independently. 2 completely different physical processes, one from the first minutes and one from the first 400,000 years, agree on how badly the balance was tipped. So the imbalance is real, precisely quantified and unexplained. In 1967, Andrei Sakharov set out what any explanation would have to satisfy. He was a Soviet physicist, better known outside the field for his later work as a dissident, and the paper is short. It lists 3 conditions. First, there must be a process that violates baryon number conservation, some interaction that can turn a quantity of antimatter into matter, or create matter without creating a matching amount of antimatter. Second, there must be violation of the symmetries known as C and CP, so that matter and antimatter behave measurably differently rather than identically. Third, the process must occur while the universe is out of thermal equilibrium, because in equilibrium, any imbalance created by one reaction is undone by its reverse. Remarkably, all 3 conditions are known to be at least partially satisfiable in the real world. Baryon number violation occurs within the Standard Model itself, through processes called sphalerons which become active at very high temperatures, exactly the conditions of the early universe. Departure from equilibrium is automatic, because the universe was expanding and cooling rapidly. And CP violation is not merely theoretical, it was discovered experimentally. That discovery happened in 1964 at Brookhaven, when James Cronin and Val Fitch found that neutral kaons decay in a way that is not perfectly symmetric between matter and antimatter. The asymmetry was tiny, a fraction of a percent in a particular decay channel, and at the time it was regarded as a technical curiosity about an obscure particle. It won the Nobel Prize in 1980. CP violation has since been measured in B mesons, in D mesons, and in 2020 in neutrinos by the T2K experiment in Japan. So all 3 of Sakharov's conditions are met. The mechanism exists, and it fails, quantitatively, by an enormous margin. The amount of CP violation contained in the Standard Model is smaller than what is required to produce the observed imbalance by something like 10 orders of magnitude. A factor of 10 billion. It is not that we lack a mechanism. It is that the mechanism we have produces an imbalance 10 billion times too small to account for a universe. That gap is one of the sharpest unsolved problems in physics, and it is why enormous effort goes into searching for additional sources of CP violation, in neutrino oscillations, in the electric dipole moment of the neutron, in rare decays at the Large Hadron Collider. Nothing sufficient has been found. The leading alternative to fixing the Standard Model directly is called leptogenesis, and it is worth explaining because it is the most popular idea in the field, and it depends on something at number 2 in a different sense, the lightest particles we know of. Neutrinos have mass. That was established by the discovery of neutrino oscillation at Super Kamiokande in 1998 and at the Sudbury Neutrino Observatory in the years following, work that won the Nobel Prize in 2015. Their masses are extraordinarily small, at least 1 million times smaller than the electrons, and the most elegant explanation for why is called the seesaw mechanism. It proposes that alongside the light neutrinos we observe, there exist very heavy partners, with masses perhaps 10 to the 10th times the protons or more, and that the observed lightness is the mathematical consequence of pairing something very light with something very heavy. Those heavy partners, if they exist, would have been produced in the early universe and would have decayed. And their decays could violate CP strongly, producing an excess of leptons over antileptons. Sphaleron processes would then convert part of that lepton excess into a baryon excess, and the universe ends up with more matter than antimatter. Leptogenesis has the right structure and the right magnitude. What it does not have is a direct test, because the particles involved are far too heavy to produce in any accelerator that could be built. The only observational handles are indirect, measuring CP violation in ordinary neutrinos, which the T2K result began, and determining whether neutrinos are their own antiparticles, which is the goal of the neutrinoless double beta decay experiments now running underground in Italy, Japan, Canada, and the United States. Neither has yet delivered a verdict. Now the observational side, which is where this becomes stranger than a theoretical accounting problem. Mounted on the outside of the International Space Station since 2011 is an instrument called the Alpha Magnetic Spectrometer. It is a particle physics detector in orbit, built by a large international collaboration, and it measures the charge, mass, and energy of cosmic ray particles with a precision no balloon-borne experiment could reach. It has recorded billions of events. Antiprotons show up routinely, and they are expected. Ordinary cosmic rays colliding with interstellar gas produce them as secondary products, and the rate matches predictions reasonably well. Antihelium is a different matter entirely. To make an antihelium nucleus by collision, you would need to assemble 2 antiprotons and 1 or 2 antineutrons in the same place at the same instant with the right momenta. The predicted rate for that in ordinary astrophysical processes is essentially 0, so low that a single confirmed detection would be difficult to explain by any conventional route. The Alpha Magnetic Spectrometer has reported candidate antihelium events. In public presentations, the numbers discussed have been roughly 6 candidates consistent with antihelium-3 and 2 consistent with antihelium-4. Those results remain unpublished as detections, and the caution is entirely appropriate. The instrument sees enormous numbers of ordinary helium nuclei and a single misidentification, a sign error in charge determination caused by a scattering event in the detector, would produce exactly this signature. The collaboration has spent years on the analysis and has not claimed a discovery. It should not be presented as one. But the reason those candidate events are discussed at all, in serious venues, is what they would mean if even one of them is real. Antihelium arriving at that rate cannot be manufactured by ordinary astrophysics. The 2 available interpretations are that there are antimatter stars, anti-stars, surviving somewhere in our own galaxy, or that there is an antimatter region close enough to leak particles into our neighborhood. A search of Fermi gamma-ray data, published in 2021, extracted 14 candidate antistar sources from the catalogue of unidentified objects. None has been confirmed, and each has ordinary explanations available. A few concrete facts help calibrate how thin our direct experience of antimatter is. The total quantity of antimatter ever deliberately manufactured on Earth, across every laboratory and every decade, amounts to a few nanograms. At CERN, the ALPHA experiment has succeeded in trapping neutral antihydrogen atoms, an antiproton with a positron in orbit, and holding them for as long as 16 minutes, long enough to shine lasers at them and compare their spectra with ordinary hydrogen. The spectra match to the precision measured, as the theory requires. In 2023, the same collaboration reported the first direct test of how antimatter responds to gravity, and found that it falls downward, at the ordinary rate, closing a loophole that had been open since Dirac. Antimatter also occurs naturally in small amounts nearby. Cosmic rays hitting the upper atmosphere produce antiprotons, some of which are trapped by the Earth's magnetic field into a thin belt. Thunderstorms produce positrons. Certain radioactive isotopes emit them, which is the basis of medical imaging. None of it is exotic. It is simply rare, and it never lasts, because it is surrounded by matter. And it is worth noting how finely the imbalance was tuned, though nobody knows by what. Had the excess been 1 part in a million, rather than 1 part in a billion, the universe would contain 1,000 times more ordinary matter than it does. Structure formation would have proceeded differently. The ratio of matter to radiation would have been altered, and the resulting universe would have been denser and possibly short-lived. Had it been 1 part in a trillion, there would have been too little matter to form galaxies at all. The number that came out is not obviously special, and there is no theory that predicts it. It is simply the number the universe has, and everything downstream of it, the existence of stars, of chemistry, of anyone to ask the question, follows from it. Now the hypothetical, labeled clearly as speculation, and it is the reason this entry sits at number 2 rather than further down. There is a class of models known as inhomogeneous baryogenesis. In these models, the process that tipped the balance between matter and antimatter did not do so uniformly. The tipping was local rather than global, driven by fields that varied from place to place in the early universe, and in that case, the sign of the imbalance need not be the same everywhere. A universe that is overwhelmingly matter in our region could contain regions where the excess went the other way, made of antimatter, structured exactly as our region is, with antimatter stars and antimatter planets and, in principle, antimatter chemistry. Within the observable universe, this is strongly constrained, and the constraint is elegant. Any boundary between a matter region and an antimatter region would sit in the intergalactic medium, where gas from both sides meets. That gas would annihilate continuously along the entire surface of the boundary, producing gamma rays at a characteristic energy of about 70 mega-electron volts, the signature of neutral pion decay. Nothing like that glow has ever been detected anywhere on the sky. The resulting limits push any antimatter domain to a distance of more than about 3.5 billion light-years. That is a strong constraint, and it settles the question for the volume we can see. It says nothing whatsoever about the rest. The observable universe is a sphere 93 billion light-years across, and it is not the universe. There is no measurement of any kind available for what lies past the particle horizon, and if inflation is even approximately correct, the universe beyond it is very much larger, by factors that are difficult to write down. A domain structure with a characteristic scale larger than our horizon would be entirely invisible to us and would look exactly like what we observe, a region that is uniformly matter, all the way to the edge of vision with no boundary in sight. There is a further consequence of the domain idea that is worth following, because it turns an abstract cosmological model into something with a shape. If antimatter regions exist and are separated from matter regions by more than the distance light has traveled, then those regions have never been in contact. Nothing has crossed between them. There is no boundary in the sense of a wall, because the two regions have simply never met. What would eventually happen over enormously long timescales is that expansion carries them further apart rather than together, which means that in a universe with domain structure on scales larger than the horizon, the annihilation surface that the gamma-ray searches look for might not exist at all. The regions would be permanently separated by geometry rather than by anything physical. That is a strange kind of answer. It says the question of why there is more matter than antimatter might have a purely local answer, that our patch went one way, some other patch went the other, and there is no global asymmetry to explain, only a local one to describe. It is not a satisfying resolution because it converts a physics question into an accident of location. It is also, at present, entirely untestable, which is why it belongs in this list under the heading of speculation and not under the heading of results. What is not speculation is the shortfall. 10 orders of magnitude between the CP violation the standard model contains and the CP violation the universe evidently used. That is not a discrepancy at the edge of measurement, like a 5 sigma tension in an expansion rate. It is a gap so large that everyone agrees something substantial is missing, and no experiment has yet found it. So the honest statement of this entry is a chain of 3 sentences. The observable universe is made of matter. We do not know why, and the mechanism we have falls short by a factor of 10 billion. And the leading class of explanations for the shortfall permits the answer to be that somewhere beyond the edge of what we can see, the balance went the other way, and that the boundary between the two regions, wherever it lies, is a surface of continuous annihilation that has been burning since the first second, and which we will never observe. That answer, if it exists, is hiding somewhere in space. It is out of reach, but it is in a place, and a place is at least the kind of thing one can point at. The last entry on this list is not hiding in space at all. Number 1. The universe is changing its mind. In 1998, 2 competing teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Nobody doubted that it was slowing. The universe contains matter. Matter gravitates. Gravity pulls inward, and an expanding universe full of matter must therefore decelerate. The only open question was by how much, whether there was enough matter to eventually halt the expansion and reverse it, or whether the universe would coast outward forever, slowing but never stopping. The 2 possibilities were called a closed universe and an open universe, and choosing between them was regarded as the central observational problem in cosmology. The method was Type 1 a supernovae, the same standardizable explosions that form the top rung of the distance ladder at number 3. Find them at large distances, measure how bright they appear, compare with how bright they should be, and you have a distance. Compare that distance against the redshift, and you have the expansion history. The Supernova Cosmology Project was led by Saul Perlmutter at Berkeley. The High Z's supernova search team included Brian Schmidt and Adam Rees. They were competitors. They were using different software and different analysis choices, and they arrived at the same result within weeks of each other. The distant supernovae were too faint. Not by a large amount, somewhere between 10 and 25%, but consistently and in a pattern that could not be explained by dust or by evolution of the supernovae themselves. Too faint means further away than expected. Further away than expected means the universe expanded more in the intervening time than a decelerating model allows. The expansion is not slowing down. It is speeding up. Both teams spent months trying to find the error, because the result was not merely surprising, it was the opposite of what everyone expected. Neither found one. The result was published, confirmed repeatedly over the following years, and won the Nobel Prize in Physics in 2011. To account for it, cosmology added a component. It is called dark energy, and the name is a placeholder for ignorance, rather than a description. What it does is provide a pressure that pushes space apart. What it is remains unknown. It makes up roughly 68% of the total energy content of the universe, at a density of about 6 × 10⁻10 joules per cubic meter, which sounds enormous until you notice the units. That is a very small amount of energy in each cubic meter. It matters because there are a very large number of cubic meters, and because, unlike matter, it does not thin out as the universe expands. That last property is the crux of this entire entry, and it comes down to a single parameter. The behavior of any component of the universe is characterized by its equation of state, written as W, which is the ratio of its pressure to its energy density. For ordinary matter, W is 0. Matter exerts no significant pressure, and it dilutes as the universe expands, exactly as you would expect. For radiation, W is 1/3. For a cosmological constant, Einstein's lambda, energy inherent in empty space itself, W is exactly -1. And a component with W equal to -1 does not dilute at all. Double the volume of the universe and you have twice as much of it at the same density, forever. For 25 years, -1 has been the working assumption. Everything that follows from it has become the standard account of the future. If dark energy is a constant, the acceleration continues indefinitely. Distant galaxies recede faster and faster. Eventually they cross a horizon beyond which their light can never reach us, and the observable universe empties out. Star formation dwindles as gas is exhausted. The last stars burn out. What remains cools toward a uniform, dark, thin state that persists essentially forever. That picture has been in every popular account of cosmology for a quarter of a century, and it is presented almost always as a settled fact. It was never a measurement. -1 was an assumption, a reasonable one, chosen because it is the simplest possibility and because nothing in the data required anything else. But the data was thin. Measuring whether we changes over time requires measuring the expansion history at many different epochs with high precision, and until recently, nobody could do that. It is worth knowing how badly we understand the thing whose behavior is in question, because it makes the assumption of constancy look less safe in hindsight. If dark energy is the energy of empty space, then quantum field theory should be able to calculate it. Empty space in that framework is not empty. It is filled with fields fluctuating at every scale, and those fluctuations carry energy. The calculation has been done. The answer disagrees with the observed value by a factor of about 10 to the 120th power. That is not a discrepancy in the ordinary sense. It is routinely described as the worst quantitative prediction in the history of physics, and it has been outstanding since the 1960s. We are, in other words, assuming that a quantity we cannot calculate to within 120 orders of magnitude is exactly constant. The alternatives have names. Quintessence describes dark energy not as a property of the vacuum, but as a field slowly rolling down a potential, in which case its equation of state naturally changes with time, which is precisely the behavior the data now mildly prefers. At the other extreme, a value of W below -1 is called phantom dark energy, and taken literally, it leads to a big rip, in which the accelerating expansion eventually overwhelms gravitational and even electromagnetic binding, tearing apart galaxies, then stars, then planets, then atoms, at a calculable date. The DESI fits wander across that boundary. The preferred history has view crossing -1 at some point, which is theoretically awkward, because most simple field models cannot cross it at all without introducing instabilities. Einstein's own history with the constant is often told as a joke and is worth telling accurately. He introduced lambda in 1917 to make a static universe possible, because a universe of matter alone must collapse. When Hubble's observations showed the universe expanding, the term became unnecessary, and Einstein dropped it. The remark about it being his greatest blunder is second-hand and may never have been said. What is certain is that the term he invented for the wrong reason turned out to be required 70 years later for a different reason entirely, and that its value is now the single most consequential unknown in the subject. Now somebody can. On Kitt Peak in Arizona sits the Mayall 4-meter telescope, which has been operating since 1973. In 2019, it was fitted with a new instrument called the Dark Energy Spectroscopic Instrument, universally called DESI. At its focal plane are 5,000 robotic fiber positioners, each of which can be re-aimed independently in a matter of seconds, so that 5,000 galaxies can be observed simultaneously and the whole field reconfigured before the next exposure. It has measured the redshifts of tens of millions of galaxies and quasars. Its method is baryon acoustic oscillations, which is the same physics as the sound horizon at number 3, seen from the other side. Those frozen sound waves left a preferred separation between galaxies of about 490 million light-years, a faint but real excess of galaxy pairs at that distance, imprinted everywhere. It is a ruler of known length, built into the distribution of matter, and it is present at every epoch. Measure its apparent size in a slice of the universe at one redshift, then in another slice at a different redshift, and you have measured the expansion history directly, at multiple times, rather than inferring it from a single snapshot. That is the capability nobody had before, and it is exactly what is needed to test whether we moves. The first-year results were released in April of 2024. The data released 2 results, using 3 years of data, followed in March of 2025. Both preferred a model in which dark energy evolves over one in which it does not. The evolving model is written with 2 parameters instead of 1, W0, the present-day value, and WA, which describes how it changes with time. For DESI's second data release combined with the microwave background, the preference for the evolving model runs at about 3.1 standard deviations, with best fit values of W0 around -0.42 and WA around -1.75. Combined instead with the Pantheon Plus compilation of over 1,500 supernovae, the numbers shift to W0 around -0.84 and WA around -0.62. Across the full set of dataset combinations, the reported significance ranges from roughly 2.8 to 4.2 standard deviations, and which supernova sample is used is the main axis of the ongoing argument. In July of 2026, DESI released results using the Lyman alpha forest, absorption features in quasar spectra that trace intergalactic hydrogen, extending the measurement to higher redshift than galaxies allow. The Dark Energy Survey using a different telescope in Chile and a different technique, has produced results in accord. None of this is a discovery. 3 sigma is not 5 sigma. The systematics in supernova compilations are genuinely contested, and there is an established history in cosmology of 3 sigma results evaporating. Every careful description of these results says so, and this one does too. But look at what the pattern implies, taken at face value. The preferred values describe a dark energy that was more negative than -1 in the past and is rising toward -1 now and possibly past it. In plain terms, dark energy is weakening. The push is getting smaller. And if it continues to weaken, the standard account of the future is wrong. Acceleration does not continue forever. It slows. Eventually, the outward push falls below the inward pull of gravity, expansion stops, and the universe begins to contract. Several analyses published in 2025 have run that arithmetic explicitly. A study from Yonsei University in South Korea, reported through the Royal Astronomical Society, argued for a decreasing dark energy density on the basis of supernova and baryon acoustic oscillation data together. A widely reported calculation by a Cornell physicist and collaborators put the universe roughly halfway through a total lifespan of about 33.3 billion years, continued expansion for something like another 7 to 11 billion years, a maximum size, and then contraction, ending in a big crunch, the scenario the field effectively retired in 1998. Other analyses place the end nearer 20 billion years. Every one of these numbers is model-dependent and should be treated as such. What is not model-dependent is that the question is open again and that it was closed for 25 years on the basis of an assumption. Consider what the turnaround would actually look like if it comes. It is several billion years from now. The most distant galaxies still visible are still receding, still red-shifted, still moving away. Their recession has been slowing for a long time, imperceptibly, by an amount no single measurement could detect. And then the rate stops falling and begins to rise in the other direction. Nothing happens. There is no shudder, no flash, no boundary crossed. The largest event in the history of the universe, the moment expansion ends and contraction begins, passes without producing any observable signal at all. An astronomer alive at that moment, with instruments far better than ours, would need to compare measurements separated by millions of years to notice that anything had changed. The turnaround is not an event. It is a sign change in a second derivative, and it would go by in complete silence. Which brings this list to the reason this entry is first, and it is not the size of the consequence. It is the location of the answer. Every other entry on this list has an answer somewhere. The rings at number 10 will be explained by a better radio survey, and the square kilometer array is being built. The Methuselah star's age will be settled by better interior models and more astroseismology. The long-period transients will be catalogued properly once searches are written for them. Gamma-ray bursts and fast radio bursts have growing populations and improving localizations. The microwave anomalies are cosmic variance limited, which is worse, but a polarization satellite is being built to attack part of it. The highest energy particles need a larger detector, and larger detectors are proposed. The expansion rate will be settled by gravitational wave sirens within a few decades. Even the antimatter problem has laboratories working on it, and a mechanism that could, in principle, be tested. The answer to number 1 is not in a place. The parameter WA describes how dark energy changes over cosmic time. The only way to measure how something changes over cosmic time is to observe the universe over cosmic time. Everything we can do, every survey, every telescope, every instrument that will ever be built is a reading of the fossil record, the expansion history frozen into light that has already arrived. We can improve the reading enormously. What we cannot do is watch it happen. So the phrase from the beginning of this list returns, and it means something different now. The answer is further away than the object. At number 10, the object was a ring 2 billion light-years away, and the answer was further still, further in the sense of requiring better instruments and more time. Here, the object is not distant at all. Dark energy is in this room. It is in every cubic meter of space between here and the wall, at exactly the same density as it has anywhere in the universe, doing exactly the same thing. It is the least remote thing on this entire list. And its answer is the furthest away of all, because the distance is not spatial. It lies in a time. The observation that would settle whether everything continues to spread out forever, or turns around and comes back, is billions of years from being possible, and no instrument can shorten that. There is a final inversion, and it closes the list properly. Every entry above this one depends on the expansion history. The age of the oldest stars is compared against an age of the universe derived from it. The Hubble tension is a disagreement about it. The distances to the gamma-ray burst, to the fast radio bursts, to the rings, all of them are computed through it. The angular scales in the microwave background are converted into physical scales using it. If 1 is not -1, all of those numbers move. The age of the universe changes. The distance to everything changes. The sound horizon changes, and with it, the early universe expansion measurement, which means the disagreement at number 3 either narrows or widens depending on which direction the correction runs. Several of the anomalies on this list become either substantially worse or substantially better, and nobody yet knows which. Number 1 is not simply the last entry. It is the entry whose answer moves all the others. And there is something worth sitting with in how quietly this happened. There was no announcement that the fate of the universe had been reopened. There was no press conference declaring the end of the standard picture. What there was, in April of 2024, and again in March of 2025, was a preference in a statistical fit, a model with 2 parameters fitting the data somewhat better than a model with 1, at a significance too low to claim anything. A quarter of a century of confident description of the far future did not collapse. It simply became provisional, in a table, in a paper, without ceremony. That is what the edge of knowledge usually looks like. Not a wall and not a revelation. A number that was assumed, examined for the first time, and found to be moving. 3 instruments now coming online will test all of this independently within about a decade. The Vera Rubin Observatory in Chile will survey the entire southern sky every few nights and is expected to find hundreds of thousands of Type 1 supernovae, which is 100 times the current sample. Euclid, launched by the European Space Agency, is mapping the shapes of over 1 billion galaxies to measure how gravitational lensing has distorted them, which traces the growth of structure and therefore the strength of the outward push over time. The Nancy Grace Roman Space Telescope will do infrared surveys with a field of view 100 times Hubble's. Between them, the answer to whether we moves should be settled to a level nobody can argue with. That is the good news, and it is real. What none of them can do is tell us what happens next, because next is not something an instrument observes. And there is a way of holding this that has nothing to do with the mathematics. For 25 years, the far future of everything has been described with real confidence in classrooms and books and documentaries as a slow and irreversible thinning out. That description was not dishonest. It followed correctly from the best available model. But it rested on a parameter that had never been measured, only assumed, because assuming it was simpler than not assuming it, and because nothing in the data objected. The first instrument built specifically to check whether that parameter moves suggested that it does. Not conclusively, not at the level anyone would call a result, but suggestively, twice, in 2 independent data releases, corroborated by a separate survey using a different technique on a different continent. The certainty did not shatter. Nobody announced that it had been wrong. It simply became provisional, and it turns out that a quarter of a century of confidence about the fate of the universe can dissolve without making any noise at all. So the list ends where it began, with a correction to a picture. The edge of space is not a wall. It is a horizon, and a horizon is a fact about the observer rather than about the landscape. Every entry on this list has been a limit of observation rather than a limit of the universe. A ring we cannot resolve, a star whose interior we cannot model, a pulse our software was written to discard, a photon that should not have survived, a burst we cannot localize, a map we cannot remeasure, a particle whose source we cannot find, a ladder whose rungs we cannot fault, a symmetry we cannot explain, and a parameter we cannot watch. None of that is a statement about a universe that hides things. It is a statement about looking outward from inside something, with instruments made of the same material, in the small amount of time available. The universe is not withholding these answers. It is simply larger than the vantage point, and older than the observation, and still going on. Let that hold you for a while. Sleep well, and good night.